What if the story we tell ourselves about human civilization is only the final page of a much longer book, one whose earlier chapters have been torn away by time itself? Tonight, as you settle into the quiet darkness, let this question rest gently in your mind like snow falling on ancient ground. What if we were not the first? The earth beneath your feet has been spinning through space for 4.5 billion years, carrying with it secrets that dwarf our small human timeline. We measure our history in thousands of years, marking the rise of cities, the birth of agriculture, the first scratches of writing on clay and stone. But these moments, precious as they are to us, represent barely a whisper in the Earth's long conversation with time, a whisper that began when the planet was young and molten, and will continue long after our own voices fade to silence. Consider this: the ice age that we know, the one that shaped our ancestors and carved the landscapes we call home, ended only 12,000 years ago. 12,000 years. To us, this feels like deep time, like the very beginning of everything that matters. But to the Earth, it is less than a single breath. Before that breath, before those glaciers retreated and our familiar world emerged, there were other breaths, other ice ages, other warm periods when rivers flowed and forests grew in places we now call barren. And in those earlier times, in those forgotten seasons of the planet's long year, could there have been others like us? Others who looked up at the same stars we see tonight, who wondered at their place in the cosmos, who built and dreamed and left their own marks upon the world. The possibility settles over us like evening mist, neither proving nor disproving, but simply present. We imagine ourselves as the pinnacle of Earth's story, the first intelligence to emerge from the long dance of evolution. But intelligence, we now know, is not unique to us. We share this quality with dolphins who sing songs across ocean basins, with cephalopods who solve puzzles in their underwater laboratories, with corvids who use tools and remember faces across generations. If intelligence can bloom in forms so different from our own, in environments so distant from our experience, then why could it not have bloomed before us, in earlier springs of the Earth's long seasons? The rocks beneath our cities hold memories older than memory itself. They speak of times when continents drifted like slow, moving clouds across the planet's surface, when seas covered lands that are now mountains, when the very air breathed differently than it does today. These stone chroniclers have witnessed the rise and fall of countless species, have felt the footsteps of creatures whose names we will never know, whose entire evolutionary stories unfolded and concluded before the first human ancestor descended from the trees. In their patient silence, these geological witnesses offer us a humbling truth: we are not the authors of the Earth's story, but merely its most recent readers. And readers, no matter how careful, sometimes discover that pages have been lost, that chapters have been worn away by the patient editing of wind and water and time. Tonight, as you drift towards sleep, imagine those missing pages. Imagine civilizations that might have flourished during the warm periods between ice ages, their cities rising along coastlines that are now buried beneath hundreds of feet of ocean sediment. Imagine technologies that worked with principles we have forgotten or never discovered, structures built from materials that have long since returned to dust, knowledge systems that found different ways to harness the patient forces of nature. The absence of evidence, we often say, is not evidence of absence. But when we are dealing with the deep past, with stretches of time so vast that mountains can be ground to sand and new mountains raised in their place, perhaps absence itself becomes a kind of evidence. Evidence of the Earth's relentless ability to erase its own history, to bury its secrets beneath new layers of story, to transform the permanent into the impermanent with the infinite patience of geological time. And if this much can be lost to time's patient editing, what else might we have forgotten about the long conversation between consciousness and stone? Time stretches beyond our comprehension like an ocean whose far shore cannot be seen, cannot even be imagined. We stand on the beach of the present moment, watching waves of seconds and minutes wash against our feet, while behind us lies an abyss of years so deep that our minds cannot fathom its depths. The Earth holds billions of years in its memory, yet we focus our attention on a mere few thousand, like children studying the foam on a single wave while ignoring the vast waters that birthed it. In this silence of deep time, whole worlds could have risen and fallen like civilizations in dreams, leaving only dust and echoes for us to find centuries later if we knew how to listen. The silence is not empty. It pulses with possibility, with the patient rhythm of geological hearts that beat once every million years, marking time in a language we are only beginning to learn. Each layer of sediment is a sentence in this ancient text, each fossil a word, each mineral formation a paragraph in a story written by forces we can measure but barely comprehend. Consider the Precambrian, that vast stretch of Earth's youth that lasted nearly 4 billion years. 4 billion. The number dissolves on our tongues like sugar, sweet and incomprehensible. During those eons, the planet learned how to breathe, how to dream, how to cradle life in its rocky arms. Entire continents were born and died during this time. Supercontinents assembled and shattered like puzzle pieces in the hands of an absent-minded god. The very composition of the atmosphere shifted and changed, from the poisonous exhalations of early volcanism to the oxygen-rich breath that now fills our lungs. And we know almost nothing about it, almost nothing about 4/5 of our planet's existence. The silence of deep time has swallowed those ions whole, leaving us with fragments, with hints, with the geological equivalent of finding a single page torn from a library of books. What happened during those missing years? What forms of complexity arose and disappeared? What patterns of organization emerged from the chaos of early chemistry? Patterns that might have resembled what we now call intelligence, or consciousness, or something else entirely for which we have no name. The silence teaches us humility. It reminds us that our perspective is not just limited, but almost invisible when measured against the true scale of planetary time. We are mayflies trying to understand the life cycle of mountains, bacteria attempting to comprehend the migration of continents. Our entire recorded history, all of our wars and loves and discoveries and dreams, occupies less than 1% of 1% of the time that life has existed on Earth. And life itself has existed for less than 1/4 of the planet's total age. In this context, the possibility that intelligence arose before us becomes not just plausible but almost inevitable. If consciousness is a natural outcome of sufficient complexity, if awareness is something that emerges from matter when it organizes itself in certain ways, then the deep silence may not be empty at all. It may be full of voices we simply cannot hear, full of stories written in languages we have not yet learned to decipher. The rocks remember, but they remember in their own way, in their own time. They remember pressure and heat, the slow dance of continental drift, the patient accumulation of sediments grain by grain across millions of years. But do they remember intelligence? Do they hold within their crystalline structures some trace of minds that once contemplated the stars, of civilizations that rose and fell during the warm periods between ice ages, of technologies that worked with stone and wood and forces we have forgotten? The isotope signatures we find in ancient rocks tell us about temperature and atmosphere, about the rise and fall of sea levels, about volcanic eruptions and meteor impacts. But could they also tell us about intelligence, if we knew what to look for? Could the chemical fingerprints left by advanced metallurgy survive for hundreds of thousands of years, disguised as natural mineral formations? Could the environmental impacts of large-scale agriculture appear in the geological record as climate fluctuations we attribute to natural causes? The silence of deep time is not the absence of sound, but the presence of frequencies too low for us to hear, like the infrasonic calls of elephants that travel for miles beneath the threshold of human perception. The voices of ancient intelligence might still be echoing through the stone, still be rippling through the layers of sediment, still be whispering their secrets to anyone patient enough to listen, with instruments sensitive enough to detect the nearly inaudible. We sleep each night in the embrace of this silence, our brief dreams flickering like candles in a vast cathedral of time. And perhaps, in our deepest sleep, we sometimes hear those ancient voices calling across the eons, reminding us that we are not alone, that we have never been alone, that consciousness is as old as the first star that learned to shine in the darkness. But when we wake, we remember only fragments, only the feeling that something vast and patient has been watching over us, something that knows the true names of deep time. We know fossils as the preserved remains of ancient life, the delicate impressions of leaves and shells and bones pressed into stone like memories held in amber. But what if the process of fossilization could preserve more than just the physical forms of the past? What if ideas themselves could leave similar imprints, if the tools and structures of intelligence could become part of the geological record in ways we have not yet learned to recognize, geology becomes not just a record of life, but perhaps a record of mind, hidden as stone memories waiting for the right eyes to read their encrypted messages. The trilobite preserved in limestone tells us about the evolution of sight, about the first creatures to develop complex eyes capable of seeing the world in all its crystalline detail. But could there be other fossils hidden in the rock, fossils of fire and intention, fossils of consciousness itself? Consider the strange formations we sometimes find embedded in ancient stone, concretions that seem too regular to be natural, too purposeful in their geometry. Metal nodules arranged in patterns that whisper of design, crystal structures that grow in spirals and networks that seem almost architectural. We classify these as curiosities, as the beautiful accidents of chemistry and pressure working together across deep time. But what if some of them are not accidents at all? What if they are the fossilized remains of technologies we no longer recognize, tools and structures transformed by millions of years into something that looks natural to our untrained eyes? The process of fossilization requires specific conditions: rapid burial, the absence of oxygen, the slow replacement of organic material with minerals. But intelligence leaves traces in many forms. The controlled use of fire creates distinctive carbon signatures in soil. The mining of metals leaves scars in rock formations. The construction of large structures changes drainage patterns and erosion processes in ways that persist long after the structures themselves have crumbled to dust. We find evidence of ancient life in the most unlikely places. Microscopic organisms preserved in crystals billions of years old. The chemical signatures of photosynthesis locked in iron formations from Earth's youth. Amino acids that survived the journey from distant stars, embedded in meteorites like messages from other worlds. If biology can leave such persistent traces across such vast spans of time, then surely intelligence, organized, purposeful, transformative intelligence, would leave traces of its own. The hearths of our ancestors, barely 50,000 years old, still leave detectable traces in the archaeological record. The magnetic signatures of fired clay, the altered chemistry of repeatedly heated soil, the carbon isotopes that speak of controlled combustion. These fingerprints of intelligence persist across millennia. But what about intelligence that mastered fire not thousands but millions of years ago? What would their hearths look like after being compressed beneath miles of sediment? After being subjected to the transformative pressures of deep geological time? Perhaps we walk past such fossils every day without recognizing them. Perhaps the strange mineral formations we find in quarries, the unusual crystal growths we discover in caves, the metallic anomalies that puzzle geologists are actually the transformed remains of ancient technologies. Technologies that worked with principles we have forgotten, that used materials in ways we have never imagined, that left their mark on the world in languages written in stone. The Aboriginal peoples of Australia speak of the Dreamtime, a period when the ancestors walked the earth and shaped the landscape with their thoughts and actions. The rocks themselves, they say, remember these ancestral journeys. Sacred sites mark places where the creative force of intelligence touched the world so powerfully that the memory became part of the stone itself. What if this is not metaphor but literal truth? What if consciousness, when sufficiently focused and sustained, can indeed leave permanent impressions in the physical world? We are beginning to understand how life and geology intertwine in ways we never suspected. The very composition of our atmosphere was shaped by ancient bacteria that learned to harness sunlight. The limestone cliffs of Dover are built from the fossilized remains of countless microscopic organisms. The iron ore we mine was deposited by the first oxygen, producing life forms billions of years ago. Life and stone are not separate realms but part of a single, continuous system of transformation and memory. And if this is true for simple life, how much more true might it be for complex intelligence, for minds capable of planning and building and dreaming on scales that rival the forces of nature itself? The fossil record might contain not just the bones of ancient creatures, but the fossilized dreams of ancient civilizations, their hopes and fears and achievements transformed into stone, waiting for eyes wise enough to recognize intelligence in forms we have never seen before. In the quiet spaces between certainty and doubt, in the shadows cast by our own assumptions about what is possible and what is not, these fossil dreams lie sleeping. They whisper of technologies that grew like coral reefs, of cities that lived and breathed like vast organisms, of intelligences that worked with time itself as their primary medium, sculpting change across centuries and millennia with the patience of mountains and the precision of crystals growing in the dark. The Ice Age did not come gently. It arrived like a slow avalanche, a creeping transformation that reshaped continents and buried valleys beneath mountains of frozen time. Glaciers advanced like living things, patient and relentless, carving fjords from solid rock and scraping the earth clean of everything that had grown there before. They were sculptors working on a planetary scale, artists whose medium was ice and whose canvas was the entire surface of the world. These glacial rivers of ice acted like slow knives through the landscape, cutting deep grooves in bedrock, moving boulders the size of houses like pebbles, and concealing beneath their frozen weight anything that once stood in their path. When we think of the Ice Age, we imagine woolly mammoths and saber-toothed cats, the megafauna that roamed the tundra at the edges of the ice sheets. But what else might have been there, hidden beneath that crystalline veil, waiting to be revealed when the ice finally retreated? Beneath this veil may lie unspoken histories, civilizations that flourished during the warm interglacial periods, and were then buried beneath miles of ice when the climate shifted again. The ice did not discriminate in its advance. It covered fertile valleys and barren highlands with equal indifference, preserving some things in its frozen embrace while destroying others through the sheer weight of its presence. We know that ice preserves with remarkable fidelity. The bodies of Ice Age hunters emerge from melting glaciers still clutching their tools, their leather clothing intact, their last meals still identifiable in their stomachs. If ice can preserve organic matter with such precision across thousands of years, what else might be waiting in the places where ancient glaciers have not yet retreated? What structures, what artifacts, what entire landscapes might lie frozen in time beneath the ice sheets of Antarctica and Greenland? The weight of ice is almost incomprehensible. The Antarctic ice sheet contains enough frozen water to raise global sea levels by nearly 200 feet if it were to melt completely. This mass is so enormous that it actually deforms the bedrock beneath it, pressing the continental crust down into the Earth's mantle like a slow motion impact crater. The weight of the ice sheets that covered North America and Europe during the last glacial maximum was so great that the land is still rebounding upward, still recovering from the pressure that was removed when the ice melted away 10,000 years ago. This kind of pressure could compress and transform anything caught beneath it. Wooden structures would be flattened to thin layers of carbon, stone buildings would be ground to powder and mixed with glacial till. Metal objects would be deformed beyond recognition. Yet the ice itself might preserve the shapes, the outlines, the ghost impressions of whatever lay beneath, like a vast three-dimensional photograph exposed over millennia. The retreat of the ice revealed landscapes that had been hidden for tens of thousands of years. Valleys that had been carved by ancient rivers, now filled with glacial debris. Plains that had been scraped clean of soil and vegetation. Lakes that formed when ice dams broke and released torrents of meltwater that carved new channels across the land. This was a world remade, a palimpsest of landscapes where older stories had been erased and new ones written over them in the language of ice and stone. But erasure is never complete. Even when glaciers scar the bedrock clean, they leave traces of what came before. Striations in the stone record the direction of ice flow. Erratics, boulders carried far from their source, mark the furthest advance of the ice sheets. Moraines trace the edges where glaciers paused in their retreat, leaving behind ridges of rock and debris like the margins of unfinished sentences. If civilizations existed before the ice, their traces might survive in similar ways, fragments scattered across the landscape, patterns visible only when viewed from above, anomalies in the geological record that speak of purposeful human activity, buried and dispersed by the advancing ice. The challenge would be learning to read these traces, learning to see intelligence in the randomness of glacial till, learning to recognize the signatures of consciousness mixed with the natural debris of retreating ice. The indigenous peoples of the Arctic have stories of lands that existed before the ice, of green valleys and flowing rivers in places that are now frozen wastes. They speak of cities beneath the ice, of ancestors who retreated deeper into the frozen world as the surface became uninhabitable. These stories, passed down through generations of storytellers, might preserve memories older than our written records, memories of times when the ice veil was just beginning to fall across the world. As climate change now causes ancient ice to melt at unprecedented rates, we are beginning to see landscapes that have been hidden for thousands of years. Patches of vegetation emerge from beneath retreating glaciers, still green after millennia of preservation. Archaeological sites appear as ice sheets shrink, revealing artifacts and structures that were covered when the climate last changed. Each summer, more of the ancient world emerges from its frozen sleep, blinking in unfamiliar sunlight. And perhaps, in the years to come, as the great ice sheets continue their retreat, we will find more than just the familiar artifacts of Stone Age hunters and gatherers. Perhaps we will find traces of something older, something more complex, something that was there before the ice veil fell across the world and transformed everything beneath it into memory crystallized in frozen time. Civilizations, like stars, must decay. This is not a failure or a tragedy, but a fundamental law of the universe, written into the very fabric of reality by forces older than galaxies. Entropy ensures that nothing built lasts forever, that all structures, whether they are made of stone or steel or dreams, must eventually return to the dust from which they came. The second law of thermodynamics tells us that energy always flows from order to disorder, from complexity to simplicity, from meaning to silence. Yet memory lingers in patterns that persist long after the structures themselves have crumbled. Isotopes in the soil hold chemical signatures of ancient activities. Strange anomalies in erosion patterns whisper of obstacles that no longer exist. The very composition of the atmosphere bears the fingerprints of life forms that died out millions of years ago, their exhalations still cycling through the air we breathe today. The half-life of memory varies with the medium. Organic materials decay in decades or centuries, metals corrode and return to ore in millennia. Stone weathers and crumbles over hundreds of thousands of years. But some forms of memory are more persistent than others. Radioactive isotopes created by nuclear processes have half-lives measured in geological time. The uranium-235 in the rocks beneath our feet has been decaying steadily for over 4 billion years, serving as a cosmic clock that measures the age of the Earth itself. If an ancient civilization had mastered nuclear technology, the isotopic signatures of their activities might still be detectable today, disguised as natural background radiation or attributed to cosmic ray bombardment, or the decay of primordial elements. The natural nuclear reactor that operated in Gabon 2 billion years ago left clear isotopic evidence of its activity, evidence that we can still read in the rocks today. If nature can create such lasting nuclear signatures, what traces might conscious intelligence leave behind? The concept of deep time transforms our understanding of what persistence means. To us, a building that stands for 1,000 years seems eternal, but to the Earth, 1,000 years is less than a moment. The Gothic cathedrals that we consider ancient monuments will not survive the next ice age. The Great Wall of China will crumble to rubble in a few 100,000 years. Even the pyramids, built to last forever, are already showing signs of the patient work of entropy, their limestone blocks slowly returning to the sandy matrix from which they were quarried. But while the structures decay, the patterns they represent can persist in other forms. The magnetic orientation of fired bricks reveals the direction of the Earth's magnetic field at the time they were made. The chemical composition of ancient mortars tells us about the materials and techniques used in construction. The microscopic traces of metals in soil can reveal the locations of buildings that have long since vanished, their foundations marked only by subtle changes in the chemistry of the Earth. Intelligence leaves its mark not just in the things it builds, but in the ways it transforms its environment. Agriculture changes soil chemistry in ways that persist for millennia. The domestication of plants and animals creates evolutionary pressures that continue long after the civilizations that began them have disappeared. The very topography of landscapes can be shaped by conscious intervention, rivers redirected, valleys terraced, forests cleared and replanted according to patterns that reflect the organizing principles of mind. These transformations become part of the geological record, integrated into the slow cycles of erosion and deposition that constantly reshape the Earth's surface. What we interpret as natural processes might sometimes be the long-term consequences of ancient intelligence, Patterns impressed upon the landscape so long ago that we have forgotten they were ever artificial. The relationship between memory and entropy is not simple opposition, but complex dance. Entropy breaks down existing structures, but it also creates the conditions for new patterns to emerge. The decay of one civilization provides the raw materials for the next. The carbon dioxide released by the decomposition of ancient forests creates the greenhouse gases that drive climate change, which in turn shapes the conditions that will determine what kinds of life can flourish in the future. Memory adapts to survive the universal tendency toward decay. Information that cannot persist in one medium finds ways to encode itself in another. The stories we tell transform to suit new audiences, but they carry forward essential truths across generations. The technologies we develop evolve to work with available materials, but they preserve core principles that transcend their specific implementations. Perhaps the deepest memories are not stored in any particular structure, but in the patterns themselves, in the relationships between things rather than in the things themselves. The way rivers flow, the way mountains rise, the way life organizes itself into ecosystems. These might be the true archives of ancient intelligence, systems so integrated with natural processes that we cannot distinguish between what was planned and what simply emerged from the patient working of physical laws. In this view, the Earth itself becomes a kind of memory palace, its landscapes and climate systems and cycles of growth and decay all bearing traces of every intelligence that has ever worked with its materials. We are not just studying the history of rocks and fossils, but reading the autobiography of consciousness itself, written in a language so subtle that we are only beginning to learn its alphabet. Wind, water, and ice act as the universe's most patient editors, revising the manuscript of the Earth's surface word by word, sentence by sentence, erasing entire paragraphs of geological history with the slow persistence of natural forces. They work without urgency or deadline, these elemental editors, taking millions of years to complete revisions that transform mountains into plains and continents into archipelagos of memory scattered across the ocean floor. Even mountains crumble in time, their granite peaks reduced to sand and carried grain by grain to distant shores. The Himalayas, thrust skyward by the collision of continents, are already being worn away by monsoon rains and glacial ice, their height measured not just in meters above sea level, but in tons of sediment deposited annually in the Bay of Bengal. What chance would a city have after 100,000 years? What trace would remain of even our greatest monuments after the patient editors of erosion had finished their work? The absence of evidence may not be evidence of absence, but rather the inevitability of erasure built into the very fabric of our dynamic planet. We expect permanence from our constructions, but the Earth recognizes no such thing. To wind and water, a skyscraper is no different from a cliff face. Both are simply configurations of matter waiting to be redistributed according to the laws of physics and the gradients of gravity. Consider the Colorado Plateau, where the Grand Canyon reveals 2 billion years of Earth history in layer upon layer of sedimentary rock. Each stratum tells a story of ancient environments, shallow seas, desert dunes, river deltas, tropical swamps. But what is most striking about this geological library is not what it contains, but what it has lost. Entire epochs are missing from the record, represented only by unconformities, gaps in the rock sequence where erosion removed millions of years of accumulated history before new layers could be deposited on top. These missing chapters in the Earth's autobiography represent more than just lost rock. They represent lost landscapes, lost ecosystems, lost possibilities for the development of complex systems that might have included intelligence. If entire mountain ranges can be erased from the geological record, leaving no trace of their existence except the sediments they became, then entire civilizations could certainly vanish in the same way. The rate of erosion varies dramatically with climate, topography, and rock type. In the humid tropics, chemical weathering can break down granite to clay in a few thousand years. In arid regions, rock formations can persist for millions of years with minimal change. The preservation potential of any ancient civilization would depend not just on what they built and how they built it, but on where they chose to build and what climatic changes occurred after they were gone. Water is perhaps the most powerful eraser of all. Rivers carry away entire continents grain by grain, cutting through the hardest rock with patient persistence. The Mississippi River transports 500 million tons of sediment to the Gulf of Mexico every year, the equivalent of moving a mountain range to the sea, piece by microscopic piece. Ocean waves undercut cliffs and carry away the debris. Salt water dissolves limestone and marble, and groundwater slowly leaches away the mineral cement that holds sandstone together. But erosion is not random destruction. It follows patterns, creates forms, leaves signatures that can be read by those who know the language. The shape of a valley reveals the history of the river that carved it. The orientation of sand dunes records the direction of prevailing winds. The distribution of boulders traces the path of ancient glaciers. Erosion destroys the original forms but creates new ones that preserve information about the processes that shaped them. This raises intriguing possibilities for reading the traces of vanished civilizations. If large structures once existed in the landscape, their removal by erosion might leave characteristic patterns in drainage networks, soil distribution, or topographic features. The absence of a mountain can be detected by the presence of the sediments it became. The location of a vanished city might be marked by anomalies in the local hydrology, places where ancient foundations still influence the flow of groundwater or the patterns of surface runoff. Indigenous peoples around the world maintain oral traditions about landscapes that no longer exist, places that were transformed by floods, earthquakes, or gradual environmental change. These stories, passed down through generations, sometimes preserve accurate descriptions of geographical features that disappeared centuries or millennia ago. They serve as cultural technologies for preserving environmental memory across timescales longer than any individual human lifetime. The Aboriginal songlines of Australia encode detailed maps of the continent in ceremonial chants that have remained unchanged for tens of thousands of years. These songs describe not just the current landscape, but traces of ancient features, rivers that no longer flow, lakes that have dried up, forests that have become deserts. They suggest that human memory, properly organized and maintained, can sometimes outlast the physical features it describes. Perhaps the most humbling aspect of erosion's editorial work is its perfect democracy. It makes no distinction between natural and artificial formations, between the products of geological processes and the creations of intelligence. Wind and water edit all manuscripts with equal thoroughness, reducing pyramids and mountain ranges to the same ultimate fate, anonymous particles in the endless circulation of matter that connects all things across deep time. And yet, in this apparent destruction, there is also a kind of preservation. The atoms that once formed ancient cities now cycle through new formations. The carbon that was once alive in prehistoric forests now moves through the atmosphere and oceans, becoming part of new life, new structures, new possibilities for organization and meaning. Erosion's eraser does not destroy but transforms, does not end stories, but translates them into new languages written in stone and water and wind. Future scientists excavating the ruins of our time may find plastic bottles buried in sediment like shells, aluminum cans compressed into metallic layers like fossil reefs, and concrete structures weathered into artificial limestone formations that speak of our brief moment as shapers of the Earth's surface. They may detect the radiation signatures of our nuclear age locked in ice cores and tree rings, the isotopic fingerprints of our industrial processes preserved in the very chemistry of the atmosphere for millions of years to come. But could we, too, be walking daily on traces of older technofossils, materials we no longer recognize as artificial because time has transformed them into forms that seem purely natural? Could the strange mineral formations we find in certain caves be the fossilized remains of ancient technologies? Could the metallic nodules scattered across some landscapes be the corroded remnants of devices whose purposes we can no longer guess? The concept of technofossils forces us to expand our definition of what fossilization can preserve. We think of fossils as the impressions of bones and shells and leaves, but technology also leaves its mark on the world in ways that can persist across geological time. The quarries from which ancient peoples extracted stone are still visible as scars in the landscape thousands of years later. The slag heaps from Bronze Age smelting operations create distinctive mineral signatures in soil. The charcoal from controlled burns alters the chemistry of forest soils in ways that can be detected centuries afterward. Modern technology creates materials that have no natural analog, Plastics are essentially artificial fossils, polymers that will persist in the environment for thousands of years, slowly breaking down into smaller fragments, but never truly disappearing. The rare earth elements concentrated in our electronic devices create chemical signatures unlike anything produced by natural geological processes. The isotopic ratios, altered by nuclear technology, will remain detectable for millions of years, long after the civilizations that created them have been forgotten. But if our technology can leave such persistent traces, then surely older technologies could have done the same. The question is not whether ancient civilizations could have left technofossils behind, but whether we have learned to recognize them when we find them. Are we looking at the remnants of forgotten technologies every time we encounter unusual mineral formations, strange crystalline structures, or metallic anomalies in rocks? The challenge is that sufficiently ancient technology might have operated on principles we don't understand, using materials we wouldn't recognize as artificial. If an ancient civilization had learned to work with biological systems, their technology might look like unusual fossil formations. If they had mastered crystalline growth processes, their devices might appear to be natural mineral specimens. If they had developed techniques for working with quantum effects or manipulating matter at the atomic scale, their artifacts might be invisible to our current analytical methods. There are hints scattered throughout the geological record of processes that don't quite fit our current understanding of natural systems. The Oklo natural nuclear reactors in Gabon operated 2 billion years ago under conditions that seem almost impossibly precise, requiring exactly the right concentration of uranium, the right amount of water, and the right geological setting to sustain controlled fission reactions for hundreds of thousands of years. While we classify these as natural phenomena, they demonstrate that complex, organized processes can operate in the Earth's crust under the right conditions. Could some of the mineral formations we find in ancient rocks be the fossilized remains of similar processes, but ones that were initiated and controlled by intelligence, rather than arising spontaneously from natural conditions? Could the precise crystal alignments we sometimes discover in certain geological formations be traces of ancient technologies that worked with crystalline properties we're only beginning to understand? The boundary between technology and biology is already blurring in our own time. We create materials using biological processes, grow structures using cellular mechanisms, and design systems that evolve and adapt like living organisms. If our descendants were to discover these biotechnological artifacts millions of years in the future, would they recognize them as products of intelligence or classify them as unusual biological fossils? This question becomes even more complex when we consider that intelligence itself might take forms we haven't imagined. Our technology reflects our particular evolutionary history, our specific sensory capabilities, our unique relationship with our environment. But intelligence that evolved under different conditions might develop technologies based on completely different principles, using materials and processes that would seem magical or impossible to us. The technofossils of such civilizations might be hiding in plain sight, classified in our museums as mineral specimens or geological curiosities because we lack the conceptual framework to recognize them as artifacts. They might be embedded in the walls of caves, scattered across desert landscapes, or lying on the bottom of ancient lake beds, waiting for minds capable of seeing technology in forms that don't match our expectations. As our own technology becomes more sophisticated, as we learn to work with materials at smaller and smaller scales, as we develop techniques for manipulating matter and energy in ways that would have seemed impossible just decades ago, we may begin to recognize similar sophistication in formations we previously dismissed as purely natural. The technofossils of ancient civilizations might reveal themselves not all at once, but gradually, as our own understanding of what technology can be expands to encompass possibilities we are only now beginning to explore. In this expanding definition of technology, the entire Earth becomes a potential archaeological site, every unusual formation a possible artifact, every anomalous process a hint that intelligence has been at work in the world for far longer than we have dared to imagine. When the great ice sheets melted at the end of the last glacial period, they released enough water to raise global sea levels by more than 400 feet, drowning vast coastlines beneath waves that advanced like slow tsunamis across continents. If an advanced culture had lived near water, As nearly all human civilizations have done throughout history, then most of its remains would now rest beneath the waves, in submerged landscapes waiting to be mapped by instruments we are only now beginning to develop. The ocean is the Earth's greatest archive, a liquid library that has been collecting and preserving the records of terrestrial life for billions of years. Sediments cascade down from continental shelves like gentle snowfalls of memory, burying whatever lies beneath layers of silt and sand and microscopic shells. The deep ocean floor is a museum where time moves slowly, where artifacts might remain undisturbed for millions of years, protected from the erosive forces that scar the continents clean. Beneath the waves lie drowned river valleys that once supported lush ecosystems, coastal plains that stretched for hundreds of miles beyond the current shoreline, and entire continental shelves that were once dry land. During the last ice age, when sea levels were at their lowest, vast areas of what is now ocean floor were exposed to air and sunlight. These were not barren wasteland but fertile territories where rivers carved channels, forests grew, and life flourished in environments that are now completely underwater. The Bering Land Bridge that allowed humans to migrate from Asia to North America was just one of many such exposed areas. Similar land bridges connected Britain to continental Europe, Australia to New Guinea, and countless islands to their neighbouring mainlands. These were not narrow corridors but broad landscapes, some larger than modern countries, where civilizations could have developed and thrived for thousands of years before being claimed by the rising seas. Archaeological discoveries in shallow coastal waters have already begun to reveal traces of these drowned worlds. Stone tools and pottery fragments emerge from underwater excavations. The remains of ancient forests, perfectly preserved by salt water and sediment, are exposed when storms shift the sand on continental shelves. Entire archaeological sites lie beneath just a few meters of water, their preservation so complete that organic materials still retain their original form after thousands of years of submersion. But these discoveries represent only the most recent layers of the ocean's archive, the artifacts deposited during the current interglacial period. Beneath these relatively shallow remnants lies a much deeper record, layer upon layer of drowned landscapes from earlier ice ages, earlier warm periods, earlier rises and falls of the sea. Each cycle of glaciation and melting has added new chapters to this underwater library, creating a stratigraphic sequence of human possibility that extends back hundreds of thousands of years. The preservation conditions in marine environments can be extraordinary. The cold, oxygen-poor waters of the deep ocean slow decay to near geological rates. Shipwrecks from antiquity emerge from underwater excavations with their wooden hulls intact, their cargo still arranged as it was when the vessels sank. If such preservation is possible for organic materials that have been underwater for mere millennia, what might survive from civilizations that were drowned tens or hundreds of thousands of years ago? The challenge is access. The deep ocean remains one of the least explored environments on Earth. We have better maps of the surface of Mars than of our own ocean floor. The pressure and darkness of the deep sea make exploration difficult and expensive, limiting our ability to search for traces of ancient human activity in the vast underwater territories where such traces are most likely to be preserved. But technology is beginning to catch up with the challenge. Autonomous underwater vehicles can now map the ocean floor in unprecedented detail, revealing topographic features that hint at artificial structures beneath the sediment. Scan sonar can detect geometric anomalies that might indicate buried foundations or constructed features. Deep-sea coring devices can extract sediment samples that preserve microscopic traces of human activity: pollen from cultivated plants, charcoal from controlled fires, metal particles from ancient smelting operations. The ocean's archive is not just passive storage, but active preservation. Deep-sea sediments contain detailed records of past climate conditions, atmospheric composition, and volcanic activity. They preserve the chemical signatures of major extinction events, the isotopic traces of meteor impacts, and the microscopic fossils of organisms that lived and died in ancient seas. Within these same sediments might lie the preserved traces of ancient intelligence, the chemical fingerprints of large-scale agriculture, the mineral signatures of metallurgy, the isotopic anomalies that might indicate controlled nuclear processes. The indigenous peoples of many coastal regions maintain oral traditions about lands that were swallowed by the sea, about cities that sank beneath the waves, about ancestors who lived in places that are now underwater. These stories, often dismissed as mythology, might preserve accurate memories of real geographical changes that occurred when sea levels rose at the end of the Ice Age. They suggest that human memory, properly maintained, can sometimes outlast the landscapes it describes. As we develop new techniques for exploring the deep ocean, as our robots become more sophisticated and our sensors more sensitive, we may discover that the greatest archaeological treasures of our planet lie not on dry land, but beneath the waves. The ocean's secret archive may hold not just the remains of the most recent human civilizations, but traces of intelligence that go back far deeper in time than we have ever dared to imagine, preserved in the patient darkness of waters that have kept their secrets for hundreds of thousands of years. Stratigraphy reads the Earth's history like a vast book written in stone, each layer a page chronicling ancient environments, extinct ecosystems, and the rise and fall of countless species across deep time. Geologists have learned to read these rocky narratives with extraordinary precision, identifying the chemical signatures of volcanic eruptions, the fossil traces of mass extinctions, and the subtle shifts in climate recorded in the composition of sedimentary layers deposited grain by grain across millions of years. But what if one thin layer, erased by erosion or misread in our interpretation, carried the fingerprints of a civilization long gone? What if the Earth is hiding a missing page in its geological diary, a stratum so brief or so altered by subsequent processes that we have overlooked its significance? The discovery of such a forgotten layer would not require dramatic monuments or obvious artifacts. It might reveal itself through subtleties, unusual isotope ratios, unexpected trace elements, or patterns in mineral distribution that suggest the influence of organized intelligence. The geological record is far from complete. Erosion removes layers faster than deposition can preserve them in many environments. Tectonic activity folds and fractures rock sequences, mixing different time periods together or burying ancient formations beneath miles of newer material. Metamorphism transforms sedimentary rocks under heat and pressure, erasing the original textures and chemical signatures that might have preserved traces of ancient life or intelligence. Even when preservation is optimal, our interpretation of geological layers depends on our ability to recognize significant patterns. We identify mass extinction events by the sudden disappearance of fossil species. We detect ancient climate changes through shifts in the isotopic composition of marine carbonates. We recognize periods of volcanic activity by distinctive ash layers scattered across continents. But these interpretations require that we know what to look for, that we have conceptual frameworks capable of recognizing the signatures we encounter. The traces of ancient intelligence might be written in languages we have not yet learned to decipher. Large-scale agriculture could leave chemical signatures in paleosol horizons that we currently attribute to natural climate fluctuations. The environmental impacts of advanced metallurgy might appear as trace element anomalies that we explain through conventional geological processes. The isotopic fingerprints of controlled nuclear reactions might be hidden within the background variations we consider normal for ancient rocks. Consider the Paleocene-Ocene thermal maximum, a period of rapid global warming that occurred 56 million years ago. This event left clear signatures in the geological record: distinctive carbon isotope ratios, unusual clay mineral assemblages, and dramatic changes in fossil communities. The conventional explanation involves massive releases of methane from oceanic sediments, but the precise trigger for this release remains mysterious. Could this thermal maximum preserve traces of ancient intelligence experimenting with planetary scale engineering, their activities disguised by deep time as a natural climatic anomaly? The concept of a forgotten layer becomes even more intriguing when we consider the resolution limits of geological dating techniques. Radiocarbon dating works well for organic materials less than 50,000 years old, but beyond that limit, the signal degrades into uncertainty. Other radiometric methods can date rocks millions of years old, but cannot resolve events that lasted less than hundreds of thousands of years. There is a gap in our temporal resolution where civilizations could rise and fall without leaving traces detectable by our current methods. Archaeological evidence suggests that complex human societies can emerge and disappear within remarkably short geological timeframes. The Maya civilization reached sophisticated levels of achievement in astronomy, mathematics, and urban planning then largely collapsed within a few centuries. The Indus Valley Civilization created extensive trade networks and urban infrastructure, then vanished so completely that we still cannot decipher their writing system. If such complex societies can become virtually invisible within recorded history, how much more invisible might they become across geological time? The forgotten layer might not be missing but misinterpreted. Geologists routinely encounter anomalous formations that don't fit standard patterns, unusual mineral assemblages, unexpected geochemical signatures, structures that seem too regular to be natural, but too ancient to be artificial by conventional dating. These anomalies are typically explained through exotic but natural processes, rare types of volcanism, unusual weathering conditions, or unique combinations of geological circumstances. But what if some of these anomalies actually represent traces of ancient intelligence, their artificial origins obscured by the transformative effects of deep time? What if the forgotten layer is not absent from the geological record, but present in forms we haven't recognized, scattered through formations we have studied for decades without realizing their true significance? The search for such a layer would require new approaches to geological investigation. Instead of looking only for the familiar signatures of natural processes, we might need to develop techniques for detecting the subtle traces of organized activity, patterns in mineral distribution that suggest intentional placement, isotopic ratios that indicate controlled chemical processes, or structural regularities that hint at artificial construction modified by millions of years of geological transformation. The forgotten layer, if it exists, would represent more than just archaeological discovery. It would fundamentally alter our understanding of intelligence in the universe, suggesting that consciousness and civilization are not recent innovations but recurring themes in the Earth's long history. It would transform our planet from a stage where intelligence appeared only recently into a palimpsest where mind has written and rewritten its story across deep time, leaving traces for those patient enough to learn the languages in which such ancient stories are preserved. Mass extinctions punctuate the Earth's history like periods at the end of vast sentences, marking the conclusion of entire chapters in the story of life on our planet. The fossil record preserves these moments of catastrophic change: the Permian extinction that eliminated 90% of marine species, the asteroid impact that ended the age of dinosaurs, the volcanic episodes that poisoned ancient atmospheres with toxic gases and fundamentally altered the chemistry of air and ocean. These extinction events remind us how fragile even the most successful life forms can be when faced with rapid environmental change. If a supercivilization existed in Earth's deep past, perhaps it too fell victim to one of these planetary catastrophes, its silence becoming part of the same story that erased giant forests, emptied ancient seas, and reset the evolutionary clock time after time across hundreds of millions of years. The Cretaceous-Paleogene extinction, which ended the dominance of dinosaurs 66 million years ago, left unmistakable signatures in rock layers around the world, concentrations of iridium and other rare elements typical of asteroid impacts, shocked quartz crystals formed by extreme pressures, and layers of debris from global firestorms that followed the impact. These geological fingerprints tell a story of almost unimaginable destruction, a civilization-ending event that transformed the entire planet within a matter of years or even months. But extinction events affect different groups of organisms in different ways. While the dinosaurs disappeared, mammals survived and eventually diversified to fill the vacant ecological niches. While many marine species vanished, others persisted and became the ancestors of modern ocean life. The selectivity of extinction suggests that survival often depends not on size or strength but on adaptability, on the ability to find refuge during catastrophic times and emerge to rebuild when conditions stabilize. Could an intelligent species survive a mass extinction event? The answer might depend on the nature of their technology and their relationship with their environment. A civilization that had spread across multiple continents or developed space-based infrastructure might weather catastrophes that would destroy more localized societies. A culture that had learned to live in harmony with natural cycles might adapt more successfully than one that depended on intensive resource extraction and environmental manipulation. Alternatively, intelligence itself might be both blessing and curse during extinction events. The same cognitive abilities that allow civilizations to manipulate their environment and build complex technologies might also make them more vulnerable to cascading system failures when environmental conditions change rapidly. A highly interconnected technological society might collapse more completely than a simple hunter-gatherer culture when key resources become unavailable or when critical infrastructure fails. The extinction events in Earth's history suggest that catastrophic change is not aberrant but normal, not exceptional but routine across geological timescales. The stable climate conditions that have supported human civilization for the past 10,000 years represent an unusually quiet period in the planet's typically more turbulent history. Before this calm interval, our ancestors survived ice ages, volcanic winters, and periods of dramatic climate fluctuation that would challenge even our current technological capabilities. If earlier civilizations existed during more volatile climatic periods, they might have developed technologies specifically designed to cope with frequent environmental disruptions. Their engineering might prioritize resilience over efficiency, durability over complexity, adaptability over specialization. The traces of such technologies might be difficult to recognize because they would be designed to weather exactly the kinds of geological processes that erase conventional artifacts from the record. The isotopic signatures of mass extinctions provide clues about their causes and effects. Volcanic events leave traces of sulfur and carbon in sedimentary rocks. Impact events scatter rare elements across continents. Climate changes alter the ratios of different isotopes incorporated into shells and bones by ancient organisms. These chemical fingerprints allow us to reconstruct the environmental conditions that prevailed during extinction crises, painting detailed pictures of atmospheric composition, ocean chemistry, and global temperature patterns. Within these same isotopic records might lie traces of intelligent responses to environmental crisis. Large-scale geoengineering projects might leave chemical signatures indistinguishable from natural processes unless we knew what specific indicators to seek. Attempts to modify atmospheric composition, redirect volcanic emissions, or deflect asteroid impacts might create isotopic anomalies that we currently attribute to purely geological causes. The fossil record shows that life has recovered from every mass extinction event, often evolving new forms more complex and diverse than those that were lost. This resilience suggests that intelligence, if it arose before our own species, might also have recovered from catastrophic setbacks, each post-extinction civilization building on whatever knowledge and infrastructure survived from their predecessors. The echoes of extinction reverberate through deep time, reminding us that the Earth has witnessed multiple ends of worlds and multiple new beginnings. In this context, our own civilization appears not as the inevitable culmination of evolutionary progress, but as one experiment among many, one attempt by intelligence to establish itself in a dynamic universe where change is the only constant and survival requires not just knowledge, but wisdom about how to live within the patient cycles of planetary transformation. Perhaps the most profound echo of extinction is its reminder that all things pass, that even the most successful adaptations eventually encounter conditions that exceed their capacity for survival. But within this humbling truth lies also hope. If life has repeatedly recovered from catastrophic losses, if intelligence has the resilience to emerge from the simplest beginnings, then perhaps consciousness itself is more durable than any of its individual expressions, destined to arise again and again, wherever conditions allow mind to kindle in the darkness of matter. From the flood stories that appear in cultures across every continent to the golden ages remembered in humanity's oldest tales, myths repeat with uncanny consistency across civilizations that had no known contact with each other. The Epic of Gilgamesh speaks of waters that covered the world. Hindu texts describe cycles of creation and destruction spanning vast ages. Aboriginal Dreamtime stories tell of ancestors who shaped the landscape in primordial times. Norse mythology recounts a twilight of the gods that ends one world and begins another. Could these stories be faint echoes of real events from before the Ice Age, memories distorted by countless generations of retelling, but preserving essential truths about humanity's deeper past? Perhaps stories hold memories longer than stone does, carrying forward fragments of actual history in the amber of narrative, preserved not in archaeological layers, but in the collective unconscious of our species. The ubiquity of flood myths is particularly striking. Nearly every culture maintains stories of great waters that once covered the earth, of humanity surviving in boats or on mountaintops, of a world washed clean and reborn. Conventional explanations suggest these stories arise from local flooding events, traumatic experiences that become mythologized over time. But the global distribution and remarkable similarity of these tales suggests they might preserve memories of actual planetary-scale flooding events. Perhaps the rapid sea level rises that followed the melting of ice sheets at the end of glacial periods. If sea level rise can be preserved in mythological memory across thousands of years, what other geological events might be encoded in humanity's oldest stories? Volcanic eruptions, earthquake sequences, climate shifts, even astronomical events like comet impacts or solar storms might have been witnessed by early humans and incorporated into mythological frameworks that allowed the memories to survive across far longer timescales than written records permit. But myths preserve more than just memories of natural disasters. They also contain stories of golden ages, of times when humanity possessed knowledge and capabilities that were later lost. Greek mythology describes successive ages of declining virtue and ability, from a golden age of wisdom and peace to the current Iron Age of conflict and ignorance. Hindu cosmology speaks of cycles spanning millions of years, with periods of enlightenment alternating with ages of darkness. Even the biblical narrative implies that humanity once possessed knowledge that was later forbidden or forgotten. These stories of decline and loss might preserve collective memories of actual civilizations that achieved levels of development comparable to or exceeding our own, then collapsed due to environmental changes, internal conflicts, or external catastrophes. The mythological framework allows traumatic historical memories to be processed and preserved in forms that remain psychologically accessible across generations, even when the specific details of the original events have been lost to time. The persistence of mythological themes across cultures suggests that human consciousness has certain universal patterns, archetypal structures that shape how we interpret and remember experience. But it also suggests that some experiences are so fundamental, so transformative, that they become part of the collective memory of our species. The myth of Atlantis, for example, appears not only in Plato's dialogues, but in various forms throughout human culture. Stories of lost continents, drowned cities, advanced civilizations that vanished beneath the waves. While Atlantis is often dismissed as pure fiction, its persistent appeal might reflect deeper psychological truths about humanity's relationship with lost knowledge and vanished possibilities. Perhaps the Atlantis myth preserves distorted memories of actual civilizations that were drowned by post-glacial flooding. Perhaps it represents our intuitive understanding that intelligence has arisen before and might arise again, that our current technological society is not the first attempt by consciousness to master the forces of nature. The Aboriginal songlines of Australia represent perhaps the most sophisticated system for preserving geographical and historical information in oral tradition. These ceremonial song cycles encode detailed maps of the continent, but they also preserve memories of landscape changes that occurred thousands of years ago, the locations of rivers that no longer flow, the outlines of lakes that have dried up, the paths of ancient coastlines now far inland from current shores. If human oral tradition can preserve accurate geographical information across such vast timescales, it might also preserve memories of human activities and achievements that occurred before written history began. The songlines suggest that properly structured narrative can serve as a storage medium for complex information, a biological library that can maintain detailed records across hundreds of generations without loss of essential content. Modern neuroscience is beginning to understand how traumatic memories can be encoded not just in individual consciousness, but in genetic expression patterns that can be transmitted across generations. Epigenetic changes caused by extreme stress or environmental challenges can affect the behavior and psychological patterns of descendants who never directly experienced the original trauma. This suggests biological mechanisms through which the memory of catastrophic events might persist in human populations long after the events themselves have been forgotten. In this context, myths and legends might represent not just cultural artifacts but biological memories, evolutionary adaptations that help our species remember and prepare for the kinds of catastrophic challenges our ancestors survived. The recurring themes of flood, fire, collapse, and renewal might be built into human consciousness because they reflect actual patterns in our planet's history. cycles of destruction and regeneration that intelligence must navigate to survive across geological timescales. Perhaps the deepest function of mythology is to preserve not just specific memories but ways of thinking about time, change, and survival that remain relevant across vast scales of experience. The myths tell us that worlds end and new worlds begin, that knowledge can be lost and rediscovered, that intelligence must learn to work with cycles of change that extend far beyond individual lifetimes. In preserving these insights, mythology serves as humanity's longest-term storage medium, a library of deep wisdom written in stories that can survive even when all other records have crumbled to dust. Isotopes serve as nature's timepieces, atomic chronometers that tick away the eons with radioactive precision, allowing us to measure the age of rocks, fossils, and artifacts with extraordinary accuracy. Carbon-14, created continuously in the atmosphere by cosmic ray bombardment, is absorbed by living organisms throughout their lifetimes and begins to decay at a known rate after death, providing a reliable clock for dating organic materials up to about 50,000 years old. But beyond certain limits, this temporal record blurs into uncertainty. If a civilization thrived hundreds of thousands of years ago, the carbon clock may no longer remember them. Its signal faded below the threshold of detection. Lost in the statistical noise of natural background radiation, the half-life of carbon-14 is only 5–730 years, which means that after 10 half-lives, about 57,000 years, less than 0.1% of the original carbon-14 remains, making accurate dating impossible with current techniques. This temporal boundary creates a blind spot in our archaeological vision, a zone of deep time where organic materials become invisible to our most reliable dating methods. Within this blind zone, entire civilizations could have risen and fallen without leaving traces detectable by radiocarbon analysis. Their wooden structures, paper records, textile artifacts, and even their bones would have lost their isotopic signatures long ago, becoming indistinguishable from the natural background of ancient carbon cycling through the Earth's systems. Other radiometric dating techniques can reach much further into the past, but they require different materials and provide much lower temporal resolution. Potassium-argon dating can measure the age of volcanic rocks millions of years old, but it cannot detect events that lasted less than hundreds of thousands of years. Uranium lead dating reaches back billions of years, but works only with specific types of crystals formed under precise conditions. These long-term chronometers can tell us when mountain ranges formed or when continents collided, but they lack the precision to detect the brief flourishing of intelligent civilizations. The gap between the limits of carbon dating and the resolution of longer-term methods creates a zone of temporal uncertainty that spans roughly from 50,000 to several 100,000 years ago. This is precisely the time period when anatomically modern humans were spreading across the globe, when cognitive capabilities were reaching modern levels, when the first stirrings of symbolic thought and complex technology were emerging in the archaeological record. It is also the time period when climate conditions were highly variable, with rapid transitions between glacial and interglacial states creating both opportunities and challenges for developing civilizations. Within this dating gap, we must rely on other techniques to establish chronologies: thermoluminescence, dating for heated materials like pottery and burnt stone, electron spin resonance for materials that have been exposed to natural radiation, amino acid racemization for proteins in shells and bones. But these methods are often less precise than radiocarbon dating, with larger uncertainty ranges and more stringent requirements for sample preservation and environmental conditions. The limitations of our dating techniques become even more problematic when we consider that advanced civilizations might have developed technologies that interfere with natural isotopic processes. Nuclear reactions alter isotopic ratios in predictable ways. If ancient civilizations had access to nuclear technology, the isotopic signatures of their activities might either be unrecognizable as artificial or might have decayed beyond detection by the time we developed the capability to analyze them. Alternatively, sophisticated understanding of isotopic processes might have led ancient scientists to deliberately manipulate isotopic ratios as a form of long-term communication or record-keeping. Artificially enhanced concentrations of long-lived isotopes could serve as time capsules, messages embedded in the atomic structure of materials and designed to persist across geological timescales. Such isotopic messages might be waiting in museum collections of unusual minerals, their significance unrecognized because we lack the interpretive frameworks to read them. The carbon cycle itself adds another layer of complexity to isotopic dating. Carbon atoms move continuously between the atmosphere, oceans, living organisms, and geological reservoirs through processes that can alter isotopic ratios in ways unrelated to radioactive decay. Volcanic eruptions release ancient carbon with altered isotopic signatures. Changes in ocean circulation patterns affect the distribution of carbon isotopes between surface and deep waters. Even human activities like fossil fuel combustion have begun to alter the baseline isotopic composition of atmospheric carbon. These fluctuations in background isotopic ratios mean that apparent ages derived from carbon dating can be systematically offset from true ages by thousands of years. Calibration curves attempt to correct for these effects by comparing radiocarbon dates with ages determined through other methods. But the calibrations become increasingly uncertain as we push toward the limits of the technique. Materials that appear to be at the edge of the dating range might actually be much older, their true ages lost in the noise of isotopic variations. The realization that our temporal vision is limited by the physics of radioactive decay adds a humbling dimension to archaeological interpretation. We can see clearly into the recent past, but our vision becomes increasingly blurred as we look deeper into time. The civilizations that might have existed in the temporal blind zone beyond carbon dating remain invisible, not because they left no traces, but because we lack the tools to detect the traces they left. Perhaps future developments in analytical chemistry will extend our temporal reach, allowing us to detect isotopic signatures that are currently below our detection limits, or to extract chronological information from materials that we cannot currently date. Perhaps new dating techniques will emerge that can bridge the gap between radiocarbon and longer-term methods, illuminating the dark zone where ancient civilizations might be hiding in plain sight. Their traces present, but unrecognizable to our current instruments and interpretive frameworks. Until then, the carbon clock continues its patient ticking, marking time in atomic decay rates that connect us to the deep past, while simultaneously limiting our ability to read the full record of intelligence on Earth. The silence beyond its range remains profound and mysterious, a temporal territory where anything might have happened, where entire histories might be waiting to be discovered by minds equipped with the tools to see beyond the current limits of isotopic time. Deserts bury ruins with the patience of geological time, grain by grain building dunes that can swallow entire cities, transforming bustling centers of civilization into gentle hills of sand that reveal no hint of what lies beneath. Oceans conceal coastal settlements beneath layers of sediment and rising waters, their preservation so complete that entire landscapes remain frozen in time beneath the waves. Jungles consume abandoned structures with aggressive biological decay, vines and roots breaking apart stone foundations, while chemical processes accelerate the return of artificial materials to their component elements. Silence is nature's way of erasing memory, its most powerful tool for editing the record of the past. Yet every grain of sand may be hiding fragments of stories too fragile for us to read with current techniques, too subtle for our instruments to detect, too transformed by time and chemistry for our minds to recognize as the remnants of intelligence and intention. The Sahara Desert, now one of Earth's most barren landscapes, was a lush grassland just 6,000 years ago, dotted with lakes and rivers that supported thriving human communities. Rock art preserved in isolated outcrops shows giraffes and elephants, where now only sand exists, evidence of how rapidly environments can transform and erase the traces of their former inhabitants. If such dramatic environmental changes can occur within recorded history, what transformations might have occurred over the hundreds of thousands of years that lie beyond our historical knowledge? Archaeological sites in desert regions reveal the remarkable preservative power of arid conditions. Organic materials that would decay within decades in humid climates can survive for millennia when protected from moisture and bacterial activity. The dry air of desert caves has preserved textiles, wood, paper, and even human bodies with extraordinary fidelity. But this preservation comes at a cost. Desert sites are often buried beneath meters of wind-blown sand, making their discovery a matter of chance rather than systematic exploration. The process of desert burial follows predictable patterns. Sand accumulates preferentially in areas sheltered from prevailing winds, the lee sides of hills, the interiors of valleys, the spaces between large rocks or structures. Over time, these protected areas fill with sediment while exposed surfaces are scarred clean by abrasive particles carried in sandstorms. The result is a landscape where evidence of past human activity becomes increasingly concentrated in buried deposits while surface traces are systematically erased. Ocean environments present different, but equally effective mechanisms for concealing the past. Continental shelves accumulate sediments at rates measured in centimeters per thousand years, slowly burying whatever lies on the seafloor beneath blankets of mud and sand. The cold, low-oxygen conditions of deep water slow decay processes to near geological rates, creating preservation conditions that can maintain organic materials for millions of years. But ocean burial is not uniform. Underwater avalanches called turbidites can bury large areas rapidly, while deep sea currents can scour other areas clean of sediments. Tectonic activity can uplift seafloor sediments to become dry land, or cause coastal areas to subside below sea level. The complex interplay of these processes creates a patchy preservation record, where some areas accumulate thick sequences of sediment, while others remain exposed to erosive forces. Tropical forests accelerate decay through biological and chemical processes that rapidly break down organic materials and even attack inorganic structures. The combination of high temperature, abundant moisture, and aggressive biological activity creates conditions where wood rots within years, metals corrode within decades, and even stone structures can be undermined by plant roots and dissolved by organic acids within centuries. Yet tropical environments also create unique preservation opportunities. Waterlogged conditions in swamps and river deltas can preserve organic materials through anaerobic burial. Rapid sedimentation during flood events can bury and protect archaeological sites. Some tropical soils develop chemical conditions that stabilize certain types of artifacts while destroying others, creating selective preservation that might preferentially maintain traces of particular technologies or materials. The silence that results from these burial processes is not the absence of information, but its transformation into forms we have not yet learned to read. Geochemical analysis can detect human activities in soils and sediments long after all visible traces have disappeared. The isotopic signatures of agriculture, metallurgy, and controlled combustion can persist in buried deposits for hundreds of thousands of years. Microscopic particles of artificial materials can survive in sedimentary sequences even when the original structures have completely decomposed. The challenge is developing techniques sensitive enough to detect these subtle traces and intelligent enough to distinguish artificial signatures from natural processes that can create similar chemical patterns. Advanced analytical methods are beginning to reveal human activities in archaeological contexts where conventional excavation finds no visible artifacts. Environmental DNA extracted from ancient sediments can identify species that were present at specific times and places. Isotopic analysis of trace elements can reveal patterns of resource extraction and processing that indicate technological activities. These emerging techniques suggest that the silence of sand and sediment might not be as complete as it appears. The stories buried beneath desert dunes and ocean sediments might still be readable to sufficiently sensitive instruments and sufficiently patient investigators. Each grain of sand, each particle of mud, might carry molecular-scale information about the activities that occurred before burial transformed landscapes and erased surface evidence. The silence speaks in frequencies below the threshold of our current hearing. In chemical languages we are only beginning to understand, in temporal rhythms that span geological ages. As our analytical capabilities become more sophisticated, as our understanding of preservation processes becomes more complete, we may discover that silence itself is a form of communication, a way that the Earth preserves information about intelligence across timescales far longer than any individual civilization, any written record, any monument built to outlast the ages. In learning to read the silence, we might discover that memory takes forms we never imagined, that intelligence leaves traces in media we never considered, that the past speaks to us in voices so quiet and subtle that only the most careful listeners can hear the stories whispered by wind, scattered sand, and patient sediment. Scattered across the archaeological and geological records lie curious fragments that don't quite fit our current understanding of the past artifacts. that seem too sophisticated for their assigned ages, structures that display engineering principles supposedly unknown to their builders, isotopic signatures that suggest processes we didn't think were possible without modern technology. These anomalies appear like puzzle pieces from different boxes, each one individually explicable through conventional theories, but collectively hinting at patterns we have not yet learned to see. Are they coincidences, the inevitable result of discovering unusual examples within the vast diversity of natural and human processes? Or are they fragments of a bigger picture we have not yet assembled? Traces of knowledge systems and technological capabilities that operated according to principles we have forgotten or never discovered. The interpretation of anomalies requires careful balance between healthy skepticism and openness to possibilities that might challenge our current frameworks for understanding the past. The Antikythera mechanism, discovered in a Roman shipwreck, demonstrates the kinds of surprises that await careful investigation of seemingly impossible artifacts. This bronze device, initially dismissed as a simple astrolabe, proved upon detailed analysis to be an extraordinary astronomical computer capable of predicting eclipses and tracking the movements of planets with remarkable precision. Its discovery forced historians to revise their understanding of ancient Greek technological capabilities, revealing levels of mechanical sophistication that had been thought impossible for that time period. If such advanced devices could exist in the relatively recent past without leaving clear traces in the historical record, what other technologies might have been developed and lost during earlier periods? The Antikythera mechanism suggests that individual artifacts can preserve knowledge and capabilities that were not widely distributed, that advanced understanding can exist within civilizations without becoming part of their general technological infrastructure. Geological anomalies present similar interpretive challenges. The natural nuclear reactors of Oklo operated 2 billion years ago under conditions that seem almost impossibly precise, requiring exactly the right isotopic composition of uranium, the right amount of water moderation, and the right geological containment to sustain controlled fission reactions. While these reactors are universally accepted as natural phenomena, they demonstrate that complex, organized processes can occur in Earth's crust under specific conditions. Could other geological formations that we interpret as natural phenomena actually preserve traces of ancient technological activities? Could unusual mineral distributions reflect mining and processing operations conducted hundreds of thousands of years ago? Could distinctive crystalline structures result from manufacturing processes rather than natural crystal growth? The challenge is developing criteria for distinguishing between natural processes that produce seemingly artificial results and artificial processes whose traces have been altered by deep time into forms that appear natural. Isotopic anomalies provide particularly intriguing examples of potentially significant patterns. Variations in the ratios of different isotopes can reveal information about temperature, atmospheric composition, biological activity, and geological processes during the time when materials formed. But isotopic ratios can also be altered by nuclear reactions, controlled chemical processes, and large-scale environmental modifications that might indicate technological activities. Some researchers have identified isotopic signatures in ancient rocks that are difficult to explain through known natural processes. Unusual concentrations of rare isotopes, distinctive ratios that don't match expected natural patterns, or sudden changes in isotopic composition that coincide with other geological anomalies. While these anomalies are typically explained through exotic but natural processes, they might also preserve traces of ancient technologies that worked with nuclear reactions or large-scale chemical processes. The interpretation of anomalies is complicated by our limited understanding of the full range of natural processes that can occur in Earth's complex systems. New discoveries regularly reveal natural phenomena that were previously thought impossible: bacteria that survive in conditions once considered incompatible with life, geological processes that operate at scales and rates that challenge existing theories, chemical reactions that occur spontaneously under conditions that seem unlikely to support them. This expanding understanding of natural possibilities makes it increasingly difficult to identify truly anomalous phenomena that require explanation through non-natural causes. Each apparent anomaly must be evaluated against an evolving background of natural processes that are themselves often stranger than fiction. The line between the merely unusual and the genuinely impossible becomes increasingly difficult to draw as our knowledge of natural systems becomes more comprehensive. Perhaps the most significant anomaly is the pattern of anomalies themselves. Individual unusual artifacts or formations might be explicable as natural curiosities or measurement errors, but the existence of multiple anomalies across different time periods, geographical regions, and types of evidence suggests the possibility of systematic patterns that our current interpretive frameworks are not equipped to recognize. The puzzle of anomalies challenges us to develop new approaches to evidence evaluation that can distinguish between genuinely significant patterns and the inevitable statistical outliers that appear in any large dataset. It requires us to balance rigorous skepticism with openness to possibilities that might revolutionize our understanding of intelligence and technology in Earth's deep past. As our analytical techniques become more sophisticated, as our databases of comparative information become more comprehensive, we may discover that some anomalies resolve into natural phenomena, while others reveal themselves as parts of larger patterns that point toward forgotten chapters in the story of consciousness on Earth. The puzzle pieces may eventually assemble into pictures we never expected, revealing that intelligence has been experimenting with the possibilities of matter and energy for far longer than we have dared to imagine. Earth renews itself through cycles of creation and destruction that operate on timescales so vast they dwarf human comprehension, erasing and rewriting the surface of the planet with the patient persistence of geological forces that recognize no distinction between natural formations and the products of intelligence. Mountains rise from tectonic collisions and are worn away by erosion. Seas expand and contract as ice sheets grow and melt. Climates shift between ice ages and warm periods, transforming forests into deserts and grasslands into tundra across cycles that span hundreds of thousands of years. With every cycle, the planet erases its surface memory, leaving us with geological amnesia that conceals whatever civilizations might have flourished during earlier phases of these endless transformations. The Earth we inhabit today is not the same planet that existed during previous interglacial periods. The coastlines have shifted, the river systems have been rerouted, the soil profiles have been stripped away and redeposited according to the patient editing of wind and water and ice. This planetary renewal operates through mechanisms so pervasive that they affect every square meter of the Earth's surface over sufficient time periods. Glacial cycles advance and retreat across continents, scraping bedrock clean and depositing the debris as moraines and outwash plains hundreds of miles from their sources. Volcanic activity resurfaces vast areas with fresh lava flows and ash deposits that bury whatever existed before. Tectonic forces fold and fracture the crust, raising seafloor sediments to become mountain ranges while causing continental margins to subside beneath the waves. The sedimentary record preserves evidence of these renewal cycles in stratigraphic sequences that reveal repeated episodes of erosion and deposition, burial and exposure, transformation and redistribution. But the same processes that create these records also ensure that older records are systematically destroyed. Each new cycle of sedimentation buries and compresses earlier deposits. Each period of uplift and erosion removes layers that had accumulated during previous cycles. The concept of planetary amnesia suggests that the Earth's capacity for preserving information about its past has natural limits determined by the rates of surface processes and the timescales over which they operate. Beyond certain temporal thresholds, the physical traces of events become increasingly difficult to detect, not because they were insignificant when they occurred, but because the mechanisms of planetary renewal have systematically erased them from the accessible record. This amnesia is not uniform across all environments or all types of evidence. Some geographical regions are more tectonically stable than others, preserving older rock formations and archaeological sites that would have been destroyed in more active areas. Some types of materials are more resistant to weathering and erosion than others, surviving longer under conditions that would rapidly destroy more vulnerable substances. Some preservation environments, like permanently frozen ground or deep ocean basins, can maintain records across much longer timescales than surface environments subject to frequent disturbance. But even the most stable preservation environments are not permanent. Continental cratons that have remained relatively unchanged for billions of years still experience slow rates of erosion and chemical weathering that gradually alter their composition and structure. Deep ocean sediments accumulate continuously, but they are also subject to submarine landslides, current erosion, and eventual subduction into the Earth's interior through plate tectonic processes. The amnesia extends beyond physical traces to include chemical and isotopic signatures that might preserve evidence of ancient activities. Radioactive decay reduces the concentrations of unstable isotopes below detection limits over time. Chemical weathering alters mineral compositions in ways that can erase original signatures of formation conditions. Biological processes cycle elements through different reservoirs in ways that can obscure the original sources and timing of their introduction into environmental systems. Yet planetary amnesia is not complete erasure but transformation. The materials that composed ancient mountains become the sediments that form new rock layers. The carbon that was once incorporated into prehistoric organisms continues to cycle through atmospheric, oceanic, and biological reservoirs. The isotopic signatures of ancient processes become mixed with newer signatures in complex patterns that preserve information about past conditions in forms that are difficult to decipher, but not entirely lost. This perspective suggests that the Earth retains memory of its past not in discrete, readable records, but in the statistical patterns of ongoing processes, the accumulated effects of countless cycles of change and renewal that have shaped the current state of planetary systems. The challenge is learning to read these distributed, transformed memories, to extract information about ancient conditions and processes from the complex patterns that result from their long-term evolution. Perhaps the most profound aspect of planetary amnesia is its reminder that change, not stasis, is the natural condition of Earth systems. The stable climate and geography that have supported human civilization represent a brief moment of relative quiet in the planet's typically more turbulent history. The landscapes we consider permanent are actually temporary configurations of matter and energy that will inevitably be reorganized according to the ongoing cycles of planetary renewal. In this context, civilizations may come and go unnoticed within the vast rhythms of geological change, their traces erased not by any particular catastrophe, but by the simple passage of deep time and the patient operation of processes that recognize no fundamental distinction between artificial and natural formations. The Earth's amnesia is not forgetfulness but transformation, not loss but change, not ending but endless beginning as matter reorganizes itself into new patterns that will themselves be temporary expressions of forces that operate according to timescales far longer than any individual memory, any particular civilization, any specific arrangement of intelligence and matter that thinks it might endure forever in a universe built on the foundations of permanent change. We search diligently for bones to tell the stories of creatures that lived and died in ancient times, carefully extracting fossilized remains from rock matrices and reconstructing entire ecosystems from fragments of calcium phosphate that preserve the shapes of organisms millions of years after their soft tissues returned to dust. But what if civilizations also left bones behind? Not biological remains but structural traces carved into the bedrock itself, permanent modifications to the planet's anatomy that outlast any surface construction. These scars in the Earth might outlive memory itself, quarries where ancient peoples extracted building stone, mines that followed ore veins deep into mountainsides, reshaped river channels that continued to influence drainage patterns long after the civilizations that modified them had been forgotten. The bones of ancient intelligence might be written in the very topography we take for granted, in landscapes we assume are entirely natural, but which might actually preserve the signatures of purposeful intervention in the Earth's systems. Modern mining operations create distinctive signatures that will persist in the geological record for millions of years. Open pit mines remove entire mountains, creating artificial canyons that alter local weather patterns and drainage systems. Underground mines create networks of tunnels and chambers that can collapse to form subsidence patterns visible from space. Tailings piles accumulate unusual concentrations of trace elements that will remain detectable long after the original mining infrastructure has been reclaimed by natural processes. If contemporary mining leaves such persistent traces, then surely earlier civilizations that extracted metals, stone, or other materials would have left similar marks on the landscape. The challenge is learning to distinguish between artificial modifications and natural features that can create superficially similar patterns. Natural processes can create formations that look like quarries, caves that resemble mining tunnels, and mineral concentrations that appear artificial. But detailed analysis might reveal subtle differences in geometry, chemical composition, or geological context that could distinguish between natural and artificial origins. Ancient river diversions might be particularly persistent traces of large-scale engineering projects. Rivers naturally change their courses over time through processes of meandering, channel migration, and avulsion. But artificial channel modifications often create patterns that differ from natural river evolution in detectable ways. Straight segments, unusual channel geometries, or diversions that seem to violate natural hydraulic principles might preserve evidence of ancient water management systems. The terraforming of landscapes for agriculture could leave equally persistent signatures. Large-scale terracing operations create distinctive topographic patterns that can survive for thousands of years after agricultural activities cease. Irrigation systems alter soil chemistry and hydrology in ways that influence plant communities and erosion patterns long after the original canals have been filled in. Even the selective removal of forests or the introduction of non-native species can create ecological patterns that persist across multiple natural succession cycles. Megalithic structures represent perhaps the most obvious category of artificial bones. Embedded in the Earth's anatomy, stone circles aligned menhirs and constructed burial mounds create geometric patterns in the landscape that clearly indicate intelligent intervention. But these monuments might represent only the most visible traces of ancient earth-moving activities. Less obvious modifications, raised platforms, artificial hills, deliberately shaped valleys, might be much more common, but harder to recognize without careful topographic analysis. Some researchers have proposed that certain mountain ranges and valley systems display geometric regularities that seem unlikely to result from natural erosion patterns alone. While these claims are highly controversial and generally attributed to the human tendency to see patterns in random data, they raise intriguing questions about how we might recognize large-scale landscape modifications if they existed. Would artificial mountains be distinguishable from natural ones after millions of years of weathering and erosion? The concept of geological bones becomes even more intriguing when we consider subsurface modifications that might be completely invisible from the surface. Underground cities, tunnel networks, and subterranean storage facilities could create hollow spaces within bedrock that persist long after surface access points have been sealed or forgotten. Cave systems with artificial modifications might be indistinguishable from natural caves unless detailed analysis reveals tool marks, geometric regularities, or other indicators of intelligent construction. Geophysical surveys designed to map subsurface structure for oil exploration or mineral prospecting sometimes encounter anomalies that don't fit expected geological patterns. Unusual void spaces, geometric arrangements of different rock types, or mineral distributions that seem artificially regular are typically explained through exotic but natural geological processes. But some of these anomalies might actually represent traces of ancient subsurface engineering projects whose original purposes have been lost to time. The search for geological bones requires expanding our definition of what constitutes an archaeological site. Instead of looking only for portable artifacts and architectural remains, we might need to consider entire landscapes as potential archaeological features. This approach would require collaboration between archaeologists, geologists, and geophysicists to develop techniques for recognizing artificial modifications to natural systems and distinguishing them from the countless ways that natural processes can create apparently purposeful patterns. Perhaps most importantly, the concept of Earth's bones reminds us that intelligence always works with and through natural systems rather than in opposition to them. The most sophisticated ancient engineering might be precisely that which worked so harmoniously with geological processes that its traces have become indistinguishable from natural features. The bones of ancient civilizations might be hidden in plain sight, integrated so completely with the planet's anatomy that we walk over them daily without recognizing their artificial origins, reading them as natural formations because we have not yet learned to see intelligence in forms that transcend our current understanding of what technology looks like when it learns to work with geological time rather than against it. Climate cycles shape the rise and fall of cultures with the inexorable power of planetary forces determining which regions remain habitable, which crops can be cultivated, and which technologies become necessary for survival during periods of environmental change that can transform the entire character of civilizations within a few generations. Shifts in rainfall patterns, the advance and retreat of ice sheets, and variations in temperature determine not just individual survival, but the survival of entire ways of life, entire systems of knowledge, entire approaches to organizing human society in response to environmental conditions. But could climate not only destroy civilizations, but have destroyed others before us, long before the ice age we know from our recent history? Could the climate changes we consider natural actually preserve traces of earlier civilizations, attempts to modify their environments, their successes and failures written in the atmospheric and geological record as isotopic signatures we misinterpret as purely natural phenomena? The relationship between human activity and climate change operates through complex feedback mechanisms that can amplify small initial changes into major environmental transformations. Deforestation alters regional rainfall patterns by reducing evapotranspiration and changing surface albedo. Large-scale agriculture releases carbon dioxide and other greenhouse gases that affect global temperature patterns. Urban heat islands create local climate anomalies that can influence regional weather systems. If modern human activities can measurably alter climate systems, then surely earlier civilizations that achieved comparable scales of environmental modification could have left similar traces in the paleoclimate record. The challenge is learning to distinguish between natural climate variations and those that might have been influenced by intelligent intervention in environmental systems. Ice cores from Greenland and Antarctica preserve detailed records of atmospheric composition over the past several 100,000 years, revealing natural variations in carbon dioxide, methane, and other trace gases that reflect changing climate conditions. But these same records might also preserve evidence of ancient atmospheric engineering projects, attempts to modify global climate through large-scale manipulation of greenhouse gas concentrations or atmospheric chemistry. Sudden changes in atmospheric composition that paleoclimatologists attribute to natural causes, volcanic eruptions, changes in ocean circulation, or variations in solar radiation, might sometimes reflect artificial interventions in climate systems. Advanced civilizations might have attempted to prevent ice ages, mitigate the effects of volcanic winters, or modify regional weather patterns through technologies whose isotopic signatures have been misinterpreted as natural phenomena. The timing of past climate changes provides intriguing correlations with periods when advanced civilizations might have existed. Several major climate transitions occurred during the late Pleistocene, when anatomically modern humans were spreading across the globe and developing increasingly sophisticated technologies. Some of these transitions happened more rapidly than current models of natural climate change predict, suggesting the possibility of additional forcing mechanisms that have not been identified. Methane concentrations in ice cores show unusual fluctuations during certain periods that are difficult to explain through known natural sources. While these anomalies are typically attributed to changes in wetland area or wildfire frequency, they might also reflect large-scale agricultural activities or industrial processes that released methane into the atmosphere. Ancient civilizations that developed biotechnology or chemical industries might have produced greenhouse gas emissions comparable to those of modern industrial society. Ocean sediment cores reveal similar patterns of atmospheric and environmental change preserved in the chemistry of marine organisms and the mineral composition of seafloor deposits. These records extend much further back in time than ice cores, potentially preserving evidence of climate modifications that occurred hundreds of thousands or even millions of years ago. But the temporal resolution of marine records is generally lower than that of ice cores, making it more difficult to detect short-term climate interventions. The concept of climate modification by ancient civilizations becomes more plausible when we consider that many traditional societies developed sophisticated understanding of local weather patterns and environmental cycles. Aboriginal Australians practice fire management techniques that influence regional climate through controlled burning designed to maintain ecosystem health and prevent catastrophic wildfires. Similar traditional practices around the world demonstrate that human societies can develop technologies for environmental modification that work with natural systems rather than against them. Scaled up to civilizational levels, such environmental management practices might have achieved effects comparable to modern geoengineering proposals. Large-scale afforestation or deforestation projects could alter regional precipitation patterns. Massive irrigation systems could change local humidity and temperature conditions. Even the selective breeding of crops and domesticated animals could influence atmospheric chemistry through changes in methane production and carbon sequestration. The collapse of ancient civilizations might have left distinctive signatures in paleoclimate records as their environmental modifications were abandoned and natural systems reasserted their equilibrium states. The sudden cessation of large-scale agriculture, the reforestation of abandoned settlements, and the breakdown of water management systems could create rapid changes in local and regional climate that would be preserved in geological and biological archives. Perhaps most intriguingly, climate cycles themselves might have been influenced by intelligence in ways that created positive feedback loops between environmental modification and cultural development. Civilizations that successfully modified their local climates might have created conditions that supported larger populations and more advanced technologies, which in turn enabled even more ambitious environmental projects, until natural climate cycles or other factors disrupted the systems they had created. In this view, the paleoclimate record becomes not just a history of natural environmental change, but a potential archive of ancient geoengineering projects, successful and failed attempts by intelligence to work with and modify the Earth's climate systems. The hidden hands of climate might include not only the familiar natural forces of orbital cycles, solar variation, and geological processes, but also the intentional interventions of civilizations that learn to see climate as a planetary system that consciousness could learn to influence, guide, and perhaps even control. Evidence scattered throughout the geological record speaks of ancient impacts and global fires that suggest catastrophic resets of planetary systems. Events so destructive they could end civilizations not through the slow decay of entropy, but in sudden firestorms that left only ash and altered isotopes behind. The Cretaceous-Paleogene boundary preserves traces of the asteroid impact that ended the age of dinosaurs. Layers of iridium, rich clay shocked quartz crystals, and spherules of molten rock that tell of global wildfires ignited by debris raining from space. Could civilizations have been lost not by gradual environmental change or internal collapse, but in sudden planetary catastrophes that transformed the entire surface of the Earth within years or even months? Could the firestorms of deep time have erased entire technological societies so completely that only geochemical anomalies remain to mark their passing, traces so subtle and transformed by subsequent processes that we interpret them as natural phenomena rather than the ashes of vanished worlds? The impact record preserved in Earth's crust reveals that catastrophic collisions with asteroids and comets have occurred regularly throughout planetary history, with major impacts happening roughly every few million years and smaller, but still significant impacts occurring much more frequently. Many of these impact events coincide with mass extinctions and major environmental disruptions that fundamentally altered the trajectory of biological evolution on Earth. The environmental effects of large impacts extend far beyond the immediate destruction caused by the collision itself. The Chicxulub impact that ended the Cretaceous period released energy equivalent to billions of nuclear weapons, vaporizing rock and ejecting debris into ballistic trajectories that carried molten material around the globe. As this debris rained back down through the atmosphere, it heated the air to temperatures sufficient to ignite fires across entire continents. The global firestorms that followed major impacts would have created environmental conditions incompatible with complex civilization. Atmospheric temperatures reaching hundreds of degrees, toxic smoke blocking sunlight for months or years, acid rain from vaporized sulfur compounds, and the collapse of food webs as photosynthesis ceased would have challenged the survival even of simple organisms, let alone technologically dependent societies. But the traces of these ancient firestorms are preserved in geological layers that can be read like pages in a book of planetary catastrophes. Carbon isotope signatures reveal episodes of massive biomass burning. Soot layers mark periods when global fires consumed significant fractions of terrestrial vegetation. Trace element concentrations indicate the vaporization of crustal rocks and their redistribution across continents. Within these same catastrophic signatures might lie traces of destroyed civilizations, Their remains so thoroughly mixed with natural debris that we cannot distinguish between the burning of ancient forests and the incineration of artificial structures. The carbon isotopes we attribute to wildfire might include contributions from burned cities. The trace metals we interpret as impact ejecta might include elements concentrated by ancient metallurgy. The shocked minerals we consider purely geological might preserve microscopic traces of artificial materials transformed by extreme pressures and temperatures. Volcanic supereruptions present similar scenarios of sudden, global environmental catastrophe. The Toba supervolcano that erupted 74,000 years ago ejected enough ash and sulfur compounds into the atmosphere to reduce global temperatures by several degrees for decades, creating a volcanic winter that may have reduced human populations to dangerously low levels. Earlier supereruptions were even more severe, with some depositing ash layers across entire continents and altering climate systems for centuries. The periodicity of such catastrophic events suggests that any civilization attempting to develop over geological timescales would inevitably encounter existential threats from cosmic impacts or volcanic supereruptions. The survival strategies required for such events would differ fundamentally from those needed for gradual environmental changes. Instead of adaptation and migration, survival would require either advanced warning systems and protective technologies, or the ability to rebuild civilizations from catastrophically reduced populations and infrastructure. Archaeological evidence suggests that human societies have experienced and survived regional catastrophes that provide small-scale analogues for global firestorm scenarios. The Bronze Age collapse around 1200 BCE saw the simultaneous destruction of multiple civilizations across the eastern Mediterranean, possibly triggered by a combination of climate change, internal conflicts, and natural disasters. The effects of the Lachaise volcanic eruption 12,900 years ago can be traced across Europe in archaeological layers that show sudden abandonment of settlements and changes in technology and culture. These historical examples demonstrate both the vulnerability of complex societies to sudden environmental changes and their potential resilience when sufficient populations and knowledge survive the initial catastrophe. But they also suggest that recovery from truly global catastrophes would require much longer timescales and might result in civilizations so different from their predecessors that continuity of culture and technology would be broken. The prospect of ancient firestorms raises profound questions about the persistence of intelligence on Earth across deep time. If major catastrophes occur frequently enough on geological timescales, then the development of advanced civilizations might follow cyclical patterns of emergence, development, destruction, and recovery. Each cycle might achieve different levels of technological sophistication before encountering its own catastrophic reset. The traces of such cycles might be preserved in the geological record as repeating patterns of environmental disruption followed by recovery, but the artificial components of these signatures might be indistinguishable from natural processes unless we develop new analytical techniques specifically designed to detect the remains of incinerated civilizations. The firestorms of the past might have erased entire chapters in the history of intelligence on Earth, leaving only isotopic whispers and geochemical shadows to mark the passing of worlds we never knew existed. In this perspective, our current technological civilization represents not the first emergence of intelligence on Earth, but perhaps its latest attempt to establish itself in a universe where firestorms regularly reset the conditions for complexity, where consciousness must learn to survive not just the slow erosion of entropy, but the sudden violence of cosmic catastrophes that can transform planets in moments and require millions of years for recovery. How do we measure what is no longer there? How do we quantify the volume of silence, the weight of missing evidence, the dimensions of gaps that might once have been filled with the traces of intelligence and intention? The science of absence requires new mathematics, new methodologies for detecting the signatures of vanished phenomena that left their mark not in what remains, but in the patterns of what has been systematically removed from the record by time and natural processes. This science of negative space might hold more truth about forgotten civilizations than the artifacts we actively seek, more information than the fragments we occasionally discover, more insight than the conventional archaeological evidence that forms the basis of our current understanding of the human past. The measure of absence becomes a tool for reading the invisible, for detecting intelligence in the spaces between confirmed facts, for recognizing meaning in the gaps that erosion and decay have carved from the stone record of deep time. Statistical analysis of archaeological site distributions reveals patterns that might reflect not just the locations where ancient peoples chose to live, but also the systematic biases in preservation that determine which sites survive to be discovered by modern investigators. Coastal sites are disproportionately underrepresented because sea level rise has drowned most ancient shorelines. River valley sites are often buried beneath alluvial deposits. Mountain sites may be better preserved, but were less intensively occupied. The resulting archaeological record is not a representative sample of past human activity, but a heavily filtered subset that reflects the accidents of geological preservation as much as the realities of ancient settlement patterns. When we map the distribution of known archaeological sites and compare it to the full range of environments that would have been available to past human societies, the gaps become as informative as the discoveries. Vast regions that should contain evidence of human occupation based on their environmental characteristics and geographical accessibility show remarkable archaeological silence. While some of this absence undoubtedly reflects the limitations of archaeological survey and excavation, some might also reflect the systematic removal of evidence by natural processes operating over timescales longer than the conventional archaeological record. Geochemical analysis provides tools for detecting human activities even in the absence of visible artifacts. Elevated concentrations of phosphorus in soil can indicate former settlements where organic waste accumulated. Unusual ratios of trace elements might reflect ancient metallurgy or mining activities. Changes in the isotopic composition of carbon in sediment cores can reveal episodes of large-scale burning or forest clearance that might indicate human environmental modification. But these techniques for measuring absence work only if we know what signatures to look for, and if those signatures have survived the intervening geological processes. The challenge is developing methodologies sensitive enough to detect extremely subtle traces of ancient human activity, while avoiding false positives that might arise from natural processes that can create superficially similar chemical patterns. The temporal distribution of archaeological evidence also reveals significant gaps that might reflect either the absence of human activity during certain periods or the systematic destruction of evidence from those time intervals. The archaeological record shows clear biases toward more recent time periods, with exponentially decreasing numbers of sites as we look deeper into the past. While some of this pattern undoubtedly reflects the actual growth of human populations and technological complexity over time, some might also reflect the progressive destruction of older evidence by natural processes. Particularly intriguing are the periods of apparent archaeological silence that coincide with major environmental transitions, the boundaries between glacial and interglacial periods, the intervals immediately following volcanic supereruptions, the time periods when climate systems were undergoing rapid reorganization. These gaps might reflect either human population bottlenecks during environmentally challenging periods, or the preferential destruction of archaeological evidence by the same environmental processes that created the climate transitions. The measure of absence becomes even more complex when we consider that advanced civilizations might have developed technologies specifically designed to minimize their environmental impact or to ensure the complete removal of their traces after abandonment. Archaeological sites from recent time periods show that human societies were capable of remarkably thorough site cleanup when they chose to abandon settlements permanently. If such practices were scaled up to civilizational levels, entire technological societies might have erased their own archaeological signatures as part of planned obsolescence or environmental stewardship programs. Alternatively, some civilizations might have developed technologies that worked with biological and geological processes in ways that left no permanent artificial residues. Architecture based on living systems, manufacturing processes that used only renewable biological materials, and energy systems based on renewable natural forces might create archaeological signatures indistinguishable from natural ecological processes, even when they supported complex technological societies. The science of absence thus requires us to develop new frameworks for understanding the relationship between technological sophistication and archaeological visibility. Our current assumptions about the detectability of past civilizations are based on examples from our own technological trajectory, which emphasizes permanent materials, intensive resource extraction, and large-scale environmental modification. But intelligence might follow different technological pathways that leave different types of traces or no detectable traces at all. Perhaps the most profound insight from measuring absence is the recognition that the archaeological record is not just incomplete, but systematically biased towards certain types of activities, certain types of materials, and certain types of environmental conditions. The civilizations we can detect and study might represent only those that happen to use technologies and materials that survive geological processes, that happen to live in environments where preservation conditions were favorable, and that happened to exist during time periods when conditions allowed archaeological evidence to accumulate and persist. The vast majority of human experience across deep time might be hidden in the spaces between discoveries, in the statistical gaps that reveal themselves only when we learn to read absence as carefully as we read presence, to see significance in silence as clearly as we see meaning in the fragmentary traces that accident and time have left scattered across the patient stones that remember everything and preserve almost nothing of the intelligence that once walked among them, dreaming of permanence in a universe built on the mathematics of inevitable change. Rivers reshape the landscape with patient persistence, carrying away entire continents grain by grain and depositing the debris in deltas and floodplains that become the foundations for new geographies, new ecosystems, new possibilities for life and intelligence to establish themselves in environments completely transformed by the endless circulation of water between mountains and sea. But this same process that creates fertile valleys and builds new land also serves as one of nature's most effective erasers of memory, burying the traces of past civilizations under layers of sediment, while simultaneously carrying away the physical evidence of what once existed along ancient shorelines. Civilizations that lived along rivers, as nearly all human societies have done throughout history, may have been systematically erased from the archaeological record by the same water systems that supported their development and growth. The rich alluvial soils that make river valleys ideal for agriculture also represent the accumulated debris from upstream erosion, sediments that can bury archaeological sites beneath meters of flood deposits within relatively short time periods. Modern rivers like the Mississippi transport hundreds of millions of tons of sediment annually, enough to bury archaeological sites under significant depths of new deposits within centuries of their abandonment. Ancient rivers operating under different climate conditions might have transported even larger sediment loads, particularly during periods of rapid environmental change when vegetation cover was reduced and erosion rates were accelerated by climate shifts or human activities. The archaeological record from river valley environments reveals this burial process in action. Sites dating to different time periods are found at different depths within alluvial deposits, with older sites progressively deeper beneath younger sediments. But this stratigraphic sequence also reveals significant gaps, where sites that should exist based on the environmental attractiveness of river valleys are missing from depths corresponding to certain time periods. Some of these gaps undoubtedly reflect natural variations in river behavior, periods when channels migrated away from particular locations, or when flood regimes changed in ways that made certain areas temporarily unsuitable for human occupation. But other gaps might reflect the complete burial of archaeological evidence beneath sediment loads so massive that the sites remain undetected beneath the sampling depths of most archaeological investigations. The process of river burial is not just vertical but lateral, as meandering channels cut new paths across floodplains and abandon older channels that become buried beneath point bar deposits and natural levee formation. Entire archaeological landscapes can be erased by channel migration, with sites that were once located on prominent river bluffs ending up buried beneath the beds of modern streams. But rivers are not just agents of destruction, but also of preservation. The anaerobic conditions that develop in waterlogged sediments can preserve organic materials that would decay rapidly in well-drained soils. River deposits often contain excellent preservation environments where wooden structures, textiles, and even organic artifacts maintain their integrity across thousands of years. The challenge is access. Archaeological sites buried beneath active river channels or deep alluvial deposits are difficult and expensive to investigate. Underwater excavation techniques can reach sites in shallow water, but deeply buried sites require specialized drilling and coring equipment that is not always practical for archaeological investigations. Many potentially significant sites probably remain undetected beneath river sediments because they lie beyond the reach of conventional archaeological survey and excavation methods. Advances in remote sensing and geophysical survey techniques are beginning to reveal the hidden archaeology of river systems. Ground-penetrating radar can sometimes detect buried structures beneath alluvial deposits. Magnetometry can identify hearths, kilns, and other features that created magnetic anomalies preserved in river sediments. Electrical resistivity surveys can map subsurface variations in soil composition that might indicate buried archaeological features. But these techniques work best in specific geological contexts and may not be effective for detecting sites buried beneath the thick, homogeneous sediment packages that characterize major river systems. The development of more sensitive and deeper, penetrating survey methods might eventually allow systematic exploration of the buried archaeological landscapes that lie hidden beneath river valleys around the world. Rivers also serve as archives of regional environmental history, preserving in their sediments records of past climate conditions, vegetation changes, and human activities across entire watersheds. Pollen preserved in river deposits reveals the history of forest clearance and agricultural development. Charcoal fragments record episodes of burning that might indicate human fire management or natural wildfire activity. Trace element concentrations can detect mining and metallurgy activities conducted anywhere within the watershed. These environmental archives might preserve evidence of human activities, even when the sites where those activities occurred have been completely destroyed by erosion. The chemical signatures of ancient civilizations might be scattered throughout river systems as microscopic traces mixed with natural sediments, detectable through geochemical analysis, even when no visible archaeological evidence survives. The concept of rivers as agents of forgetting becomes particularly poignant when we consider that many of the world's earliest and most advanced civilizations developed along major river systems: the Nile, the Indus, the Yellow River, the Tigris, and Euphrates. These rivers supported the development of agriculture, urban centers, and complex technologies, but they also ensured that much of the evidence for this development would eventually be carried away or buried beneath later deposits. Perhaps the most complete archaeological records of ancient riverine civilizations lie not along the rivers themselves, but in the offshore marine sediments where river-transported debris finally comes to rest. Deep sea cores from river deltas and continental margins might preserve more complete records of watershed activities than terrestrial archaeological sites, but these marine archives remain largely unexplored from an archaeological perspective. The rivers of forgetting continue their patient work today, carrying away the traces of our own civilization grain by grain, while simultaneously creating the conditions for future burial and preservation. In their endless circulation between source and sea, they embody the fundamental truth that memory and forgetting are not opposite processes, but complementary aspects of the same planetary system that ensures nothing remains unchanged while guaranteeing that transformation itself becomes a form of preservation, a way of carrying the past forward into futures that will remember it in forms we cannot yet imagine. What would a city look like after 100,000 years of abandonment, subjected to the patient editing of wind and rain and frost, to the slow chemistry of oxidation and decay, to the relentless pressure of roots and ice that crack foundations and topple walls grain by grain, until even the memory of streets and buildings has been absorbed back into the anonymous landscape? Steel would long since have returned to rust and dust, glass dissolved by acid rain into silicate components, concrete crumbled into limestone fragments indistinguishable from natural rock formations. We try to imagine these ghost cities, these invisible metropolises that might once have risen from coastlines now buried beneath hundreds of feet of ocean sediment, or from plains now scarred clean by glacial ice. But our imaginations, trained on the archaeological remains of relatively recent civilizations, struggle to envision the complete transformation that deep time works upon even the most permanent human constructions. The process of urban decay operates through mechanisms both dramatic and subtle, both sudden and inexorably slow, Buildings collapse within decades when maintenance ceases, but their foundations can persist for millennia as subtle alterations in soil chemistry and drainage patterns. Roads disappear as vegetation reclaims pavement, but their courses remain visible as lines of different plant communities that reflect the altered hydrology created by buried infrastructure. Modern studies of abandoned cities provide insights into this process of gradual erasure and transformation. Pripyat, abandoned after the Chernobyl disaster, shows how quickly nature reclaims urban spaces when human maintenance ends. Within decades, trees grow through apartment building floors, wildlife establishes territories in former shopping centers, and the geometry of streets becomes obscured by expanding vegetation. But even as the visible structures decay, the underlying urban infrastructure continues to influence local ecology in ways that might persist for centuries. Angkor, abandoned in the 15th century, demonstrates the effects of several centuries of tropical decay on sophisticated urban infrastructure. Massive stone temples still stand, but the wooden residential areas that once housed hundreds of thousands of people have vanished completely, leaving only subtle traces in soil chemistry and vegetation patterns. The extensive hydraulic systems that supported the city remain partially visible as raised earthworks and water channels, but many components have been completely obscured by jungle growth. If stone temples can be so thoroughly concealed by just a few centuries of tropical vegetation, and if wooden cities can disappear entirely within the same time frame, then what traces would remain of urban centers after the kind of time periods we are considering? The answer might be almost nothing recognizable as architecture, but potentially significant traces in the form of altered landscapes, modified hydrology, and chemical signatures in soil and sediment. Urban centers concentrate materials and modify environments in ways that can persist long after the structures themselves have disappeared. Cities import food, water, and raw materials from large surrounding areas, while concentrating waste products and manufactured goods in relatively small geographical spaces. This process creates chemical and biological signatures that can remain detectable in environmental records for thousands of years after urban abandonment. Archaeological investigations of ancient urban sites often rely more on these indirect signatures than on architectural remains. Elevated phosphorus levels indicate areas where organic waste accumulated. Concentrations of trace metals reveal locations of craft production and trade activities. Changes in pollen assemblages preserved in nearby lake sediments document the environmental impacts of urban development on regional vegetation patterns. But these techniques work best for sites that are thousands rather than tens of thousands of years old. The chemical signatures that indicate human activities become increasingly difficult to distinguish from natural background variations as time passes and natural processes redistribute and transform the original anthropogenic materials. Urban ghost cities from deep time might be detectable only through the most sophisticated analytical techniques applied to materials that show no obvious signs of human modification. The concept of ghost cities becomes even more challenging when we consider that advanced civilizations might have developed urban planning and construction techniques specifically designed to minimize long-term environmental impact. Cities built primarily from renewable biological materials, designed to be completely recyclable, or constructed using techniques that worked with rather than against natural geological processes, might leave archaeological signatures indistinguishable from natural ecological succession. Alternatively, truly advanced urban centers might have been built in environments that are inherently hostile to archaeological preservation, floating cities that left no terrestrial traces, underground cities carved from bedrock that were later filled by sediment, or nomadic cities that moved regularly and left only temporary impressions on the landscape. Such cities might have supported large populations and sophisticated technologies, while leaving virtually no detectable archaeological evidence. The search for ghost cities from deep time might require fundamentally different approaches from conventional archaeology. Instead of looking for architectural remains and artifact distributions, we might need to develop techniques for detecting the subtle landscape modifications and environmental impacts that persist long after all visible traces of urbanization have been erased by natural processes. Remote sensing technologies are beginning to reveal hidden archaeological landscapes in environments where ground survey would miss most sites. Satellite imagery can detect vegetation patterns that reflect buried structures. Geophysical surveys can map subsurface features that have no surface expression. These techniques might eventually allow systematic exploration of regions where ghost cities might be hidden beneath apparently natural landscapes. Perhaps most intriguingly, the ghost cities of deep time might still be influencing modern landscapes in ways we don't recognize. Subtle patterns in river courses, vegetation distributions, or geological formations might reflect ancient urban planning projects whose original artificial nature has been forgotten. The landscapes we consider entirely natural might actually preserve the ghosts of civilizations whose urban planners learned to work with geological and ecological processes so skillfully that their cities became indistinguishable from natural features, even as they continued to function as intended across timescales that dwarf conventional urban planning horizons. In this view, we might be living within the ghost cities of our predecessors without recognizing them, walking streets that follow ancient plans, building on foundations laid by forgotten architects, inhabiting urban systems whose original designs have been so thoroughly integrated with natural processes that they continue to function as intended millions of years after their creators vanished into the patient anonymity of deep time. Entropy speaks in the softest voice of all the fundamental forces, a whisper so quiet that it can barely be heard above the more dramatic announcements of gravity and electromagnetism, yet so persistent and pervasive that it ultimately drowns out every other conversation in the universe. This whisper tells us why memory fades, why even the greatest monuments crumble to dust, why supercivilizations that might have spanned continents and commanded the forces of nature could not escape the final law that ensures all organized systems must eventually surrender their complexity to the democracy of randomness. The second law of thermodynamics operates with perfect impartiality, making no distinction between the crystalline structure of diamond and the delicate architecture of a living cell, between the information encoded in DNA and the knowledge preserved in libraries, between the purposeful arrangement of atoms in a computer processor and the meaningful patterns of stones in ancient monuments. All organized systems contain energy gradients that entropy works constantly to eliminate, reducing differences in temperature, pressure, and chemical concentration until everything reaches the same featureless equilibrium. Yet entropy's whisper contains a paradox that makes it far more complex and interesting than simple destruction. The same processes that break down existing structures also create the conditions for new patterns to emerge. The heat death of stars provides the heavy elements that make planets possible. The decay of organic matter creates the soil chemistry that supports new life. The collapse of civilizations releases resources and knowledge that can be recombined in novel ways by successor cultures. This creative aspect of entropy suggests that the whisper we hear as the sound of endings might also be the sound of beginnings, the subtle reorganization of matter and energy that allows intelligence to emerge repeatedly from apparent randomness. Consciousness itself might be an expression of entropy's creative potential, a way that the universe explores the possibilities hidden within increasingly complex arrangements of fundamentally simple components. The timescales over which entropy operates vary dramatically with the complexity and energy content of different systems. Biological organisms maintain their organization for decades or centuries by constantly consuming energy and exporting waste heat to their environment. Technological systems can persist for thousands of years with proper maintenance and energy input. Geological formations remain stable for millions of years because their internal energy gradients change very slowly. But all of these apparently permanent structures are actually dynamic equilibria, temporary eddies in the universal flow toward maximum entropy. Mountains appear solid and eternal, but they are constantly being worn away by chemical weathering and physical erosion. Even the protons that make up atomic nuclei will eventually decay, though this process requires timescales so vast that the entire current age of the universe represents less than a moment in the lifetime of a proton. The implications of entropy for the persistence of intelligence across deep time are both humbling and liberating. Humbling because they remind us that no technological achievement, no matter how sophisticated, can permanently escape the universal tendency toward disorganization. The most advanced civilizations must eventually face the same fate as the simplest bacterial colonies. Their organized structures will decay, their information will be lost, their influence on the universe will fade to statistical invisibility, but also liberating because entropy's creative aspects suggest that intelligence itself might be more resilient than any of its particular expressions. If consciousness represents a fundamental organizing principle that emerges naturally from sufficiently complex systems, then it might arise repeatedly throughout cosmic history whenever local conditions allow the temporary reversal of entropy that complex organization requires. The whisper of entropy becomes audible in the archaeological record as the gradual degradation of information density in surviving artifacts. Recent materials preserve fine details of their original structure and composition. Ancient materials retain only the most stable aspects of their organization, with complex molecular structures simplified to basic mineral components and intricate patterns reduced to statistical averages. This progressive loss of information means that the traces of very ancient civilizations might be present in the geological record, but encoded in forms so simplified and transformed that we cannot recognize their artificial origins. The entropy, processed remains of advanced technologies might appear as unusual but apparently natural mineral formations, their original complexity reduced to subtle variations in crystal structure or chemical composition. Understanding entropy's role in the preservation and destruction of archaeological evidence might help us develop new approaches to recognizing ancient intelligence in highly degraded forms. Instead of looking for complex artifacts that preserve obvious signs of intentional design, we might need to learn to detect the statistical signatures of former complexity in materials that appear to be purely natural products of geological processes. The concept of entropy also suggests that the most persistent traces of ancient intelligence might be found not in complex artifacts but in simple, stable patterns that resist degradation over long time periods. Basic geometric relationships, fundamental mathematical constants, and universal physical principles might serve as more durable carriers of information than sophisticated technologies that require complex materials and precise manufacturing processes. Perhaps the deepest insight from entropy's whisper is its reminder that intelligence and randomness are not opposites, but partners in the cosmic dance of organization and dissolution. Consciousness emerges from random molecular interactions, but works constantly to create order from chaos. The structures that intelligence builds inevitably decay back to randomness, but the decay process releases energy and materials that make new forms of organization possible. In this view, the history of intelligence on Earth might be not a linear progression from simple to complex, but a cyclical process where consciousness repeatedly emerges, develops, and dissolves back into the entropy from which it came, each cycle contributing to the growing complexity of the planetary system that supports the emergence of new forms of intelligence in the endless conversation between order and chaos that entropy's whisper maintains across all scales of space and time. The whisper reminds us that impermanence is not a failure but a feature, not a limitation but a liberation that allows the universe to explore all possible ways of organizing matter and energy, including the temporary arrangements we call life, consciousness, and civilization that represent some of the most improbable and beautiful expressions of entropy's infinite creativity. What we study in archaeology is often not the presence of things, but their absence, not the solid reality of artifacts and structures, but the impressions they left behind when they pressed against clay, the outlines they cast in stone when they blocked the flow of sediment, the echoes they created in the environment when their presence altered the natural patterns of decay and growth. We excavate shadows more often than substances, traces more often than objects, the negative spaces where intelligence once imposed its patterns on matter that has long since returned to dust. The archaeology of shadows requires us to develop new ways of seeing, new techniques for recognizing significance in apparently empty spaces, new methods for reading the stories written in gaps and absences rather than in the conventional artifacts that fill museum displays. A post hole tells us more about ancient architecture than most of the decorative objects we recover from archaeological sites. The discolored soil where organic materials once lay reveals patterns of behavior and belief that survive long after the materials themselves have been absorbed back into the chemical cycles of the earth. Archaeological preservation operates through mechanisms that favor certain types of evidence while systematically eliminating others. creating a record that is not just incomplete, but systematically biased toward materials and activities that happen to resist the normal processes of decay. We find stone tools but not wooden handles, pottery sherds but not leather containers, metal objects but not organic textiles, creating a distorted picture of past technologies that emphasizes the durable at the expense of the perishable. But the perishable materials often leave shadows, impressions in more stable media that preserve their shapes and functions long after the original substances have vanished. Textile impressions on pottery surfaces reveal weaving patterns and decorative motifs. Wood grain preserved in metal corrosion products tells us about construction techniques and tool technologies. Even the chemical signatures of vanished organic materials can sometimes be detected in surrounding soils through sensitive analytical techniques. The concept of shadow archaeology becomes even more important when we consider the possibility of ancient civilizations whose technologies emphasized renewable, biodegradable materials rather than the permanent substances that characterize modern industrial society. A civilization that built primarily with wood fiber and other organic materials might leave archaeological shadows that are virtually invisible using conventional excavation and analysis techniques. Such civilizations might have achieved remarkable levels of technological sophistication while working exclusively with materials that return completely to natural cycles within decades or centuries of abandonment. Biotechnology based on selective breeding and genetic manipulation, architecture that grew rather than being constructed, manufacturing processes that used biological systems rather than mechanical ones. All of these approaches could support complex societies while leaving archaeological signatures that we would not recognize as artificial. The shadows of such technologies might be detectable through careful analysis of apparently natural biological and ecological patterns. Forests with unusual species distributions might preserve traces of ancient silviculture practices. Agricultural areas with persistent soil chemistry anomalies might mark the locations of intensive cultivation systems that operated according to principles we no longer understand. Even the evolutionary patterns of domesticated species might preserve information about breeding programs conducted by civilizations that have long since disappeared. Geological formations that appear entirely natural might also preserve shadows of ancient engineering projects. River channels with unusual geometric properties might follow courses established by artificial diversions. Mountain valleys with suspiciously regular profiles might have been modified by large-scale earth-moving projects. Mineral deposits with atypical distributions might reflect mining and processing activities that redistributed materials according to economic rather than geological principles. The challenge in shadow archaeology is developing analytical techniques sensitive enough to detect extremely subtle traces of artificial modification while maintaining sufficient rigor to distinguish between genuine archaeological shadows and the countless natural processes that can create superficially similar patterns. This requires interdisciplinary collaboration between archaeologists, geologists, biologists, and chemists to develop new approaches to evidence, recognition, and interpretation. Advanced remote sensing technologies are beginning to reveal archaeological shadows that are invisible to ground-based survey techniques. Satellite imagery can detect vegetation patterns that reflect buried structures or altered soil chemistry. Airborne laser scanning can map surface topography with sufficient precision to reveal earthworks that have been almost completely erased by erosion. Ground-penetrating radar can identify subsurface anomalies that indicate former human activities. But even the most sophisticated remote sensing techniques can only detect shadows that create detectable contrasts with their surrounding environments. The most complete erasure would leave no traces detectable by any currently available technology, creating archaeological silence that might conceal rather than reveal the extent of ancient human activities. Perhaps the most intriguing aspect of shadow archaeology is its suggestion that the absence of evidence might sometimes be evidence in itself. Regions that show no traces of human occupation, despite environmental characteristics that should have made them attractive to ancient peoples, might have been modified so completely that all traces of modification have been erased. The most successful ancient environmental engineering might be precisely that which worked so harmoniously with natural systems that its effects became indistinguishable from natural processes. In this view, the landscapes we consider entirely natural might actually preserve the shadows of the most sophisticated ancient technologies, engineering projects so advanced that they achieved permanent integration with geological and ecological systems. These shadow civilizations might still be functioning as intended, their cities and infrastructure so thoroughly adapted to natural processes that they continue to operate across geological timescales while remaining invisible to archaeological methods designed to detect the kinds of traces left by less sophisticated technologies. The archaeology of shadows thus becomes not just a technique for recovering lost information about the past, but a philosophy for understanding the relationship between intelligence and environment, between technology and nature, between the temporary arrangements we call civilization and the permanent patterns we call natural law. In learning to read the shadows, we might discover that intelligence has been writing its stories in the landscape far longer, and far more subtly than we ever imagined possible. Submerged landscapes hold secrets older than any surface archaeology, their preservation so complete that entire ecosystems remain frozen in the moment of their drowning, waiting beneath shifting tides for technologies sophisticated enough to read their stories without disturbing their fragile sleep. The ocean is both cradle and grave for planetary memory. Its shifting waters a curtain that hides more archaeological evidence than all the world's museums contain, more information about the deep past than all our surface excavations have revealed. When we imagine the ocean floor, we tend to picture a barren wasteland of sand and mud, but beneath the waves lie drowned river valleys that once supported lush forests, coastal plains that once stretched for hundreds of miles beyond the current shoreline, and entire continental shelves that were exposed to air and sunlight during the ice ages when vast quantities of water were locked in glacial ice. These submerged territories were not empty wilderness, but potential homelands for countless generations of humans and their predecessors. The scale of submergence is difficult to comprehend from our current perspective as sea level dwellers. During the last glacial maximum, global sea levels were more than 400 feet lower than they are today, exposing land areas equivalent to entire modern countries. The Bering Land Bridge was just one of many exposed regions. Similar connections existed between Britain and continental Europe, between Australia and New Guinea, between countless islands and their neighbouring mainlands. But the archaeological potential of these drowned lands extends far beyond the most recent ice age. Sea levels have fluctuated repeatedly throughout the past several million years, with each glacial cycle exposing and then drowning vast areas of continental shelf. Layer upon layer of formerly terrestrial landscapes lies stacked beneath the current ocean, each representing a different period when the geography of continents was fundamentally different from what we see today. The preservation conditions in marine environments can be extraordinary, particularly in deep, cold waters where oxygen levels are low and bacterial decay processes operate very slowly. Shipwrecks from antiquity emerge from underwater excavations with their wooden hulls intact, their cargo still arranged as it was when the vessels sank, organic materials preserved with a fidelity that would be impossible in terrestrial environments. If such preservation is possible for materials that have been underwater for mere millennia, what might survive from human activities that were drowned tens or hundreds of thousands of years ago? The anaerobic sediments of continental shelves might preserve wooden structures, organic artifacts, and even human remains from civilizations that existed during earlier interglacial periods when sea levels were lower than they are today. The challenge is access and detection. The deep ocean remains one of the least explored environments on Earth, more mysterious and inaccessible than the surface of other planets. The pressure, darkness, and remoteness of deep sea environments make systematic archaeological survey extremely difficult and expensive. Most underwater archaeological work focuses on shallow coastal waters where conventional diving techniques can be used, leaving the deeper mysteries of drowned landscapes virtually unexplored. But technological advances are beginning to open these underwater archives to scientific investigation. Autonomous underwater vehicles can now map the seafloor in unprecedented detail, revealing topographic features that might indicate artificial structures buried beneath marine sediments. Deep sea drilling techniques developed for oil exploration and climate research can extract sediment cores that preserve detailed records of past environmental conditions and human activities. These sediment cores from continental margins contain some of the most complete archives of regional environmental history available anywhere on Earth. They preserve pollen records that document changes in terrestrial vegetation, charcoal layers that indicate episodes of burning, and chemical signatures that reflect human activities across entire watersheds. Within these same archives might lie traces of the civilizations that created the activities recorded in the sediments. The indigenous oral traditions of many coastal peoples preserve surprisingly accurate memories of lands that were drowned by post-glacial sea level rise. Aboriginal Australians maintain detailed stories about landscapes that are now underwater, describing the locations of freshwater springs, river valleys, and other geographical features that correspond closely to what we now know about the submerged topography of continental shelves. These traditions suggest that human memory, properly organized and maintained across generations, can preserve geographical information across the entire time period since the end of the last ice age. If oral tradition can remember drowned landscapes, it might also preserve information about the human societies that inhabited those landscapes before they were claimed by rising seas. Marine archaeology is beginning to discover evidence of these drowned societies in shallow coastal waters around the world. Stone tools and pottery fragments emerge from underwater sites. The remains of ancient settlements are found beneath just a few meters of water, their preservation so complete that organic materials still retain their original structure after thousands of years of submersion. But these discoveries represent only the most accessible traces of underwater archaeology, sites in shallow water that can be investigated using conventional diving techniques. The vast majority of drowned archaeological landscapes lie in deeper water beyond the reach of current investigation methods. As technology continues to advance, as our submersibles become more sophisticated and our remote sensing capabilities more sensitive, we may discover that the ocean's secret archives contain not just the most recent chapter of human coastal occupation, but multiple layers of drowned civilizations stretching back across hundreds of thousands of years. The depth of forgotten seas might hold the key to understanding the true antiquity of intelligence on Earth, preserving in their quiet darkness the most complete records of ancient human achievement, protected from the erosion and disturbance that have destroyed most terrestrial archaeological evidence. In the patient waters that cover more than 70% of our planet's surface, the stories of forgotten peoples might be waiting in pristine condition, ready to revolutionize our understanding of how long consciousness has been experimenting with the possibilities of organized matter in the endless dance between land and sea that defines the boundaries of memory on our blue and ancient world. If civilizations are forgotten completely, dissolved by time into anonymous particles that cycle through air and water and soil without carrying any trace of their former meaning, what happens to the very concept of identity itself? When the last monument has crumbled and the final artifact has returned to dust, when even the chemical signatures of ancient technologies have been mixed beyond detection with the natural background of geological processes, does anything remain of the conscious beings who once looked up at stars and wondered about their place in the cosmos? Dust and echoes may be all that survive from even the most ambitious attempts by intelligence to establish permanent meaning in a universe governed by entropy and change. Yet within these dispersed fragments lies a profound reminder of impermanence that connects all expressions of consciousness across deep time, a recognition that our current technological civilization is not the first to face the humbling reality that nothing lasts forever in its original form, that all achievements must eventually be translated into the universal language of transformation and decay. The dust that settles on our windowsills contains atoms that were once part of mountains, dinosaurs, ancient forests, and perhaps even the structures built by civilizations whose names and purposes have been completely forgotten. These particles carry no information about their origins, no memory of their former configurations, no trace of the intentions that once organized them into tools and buildings and works of art. Yet they represent a form of physical continuity that connects us materially to everything that has ever existed on this planet. Modern analytical chemistry can sometimes trace the origins of dust particles with remarkable precision, identifying their source rocks, the weathering processes that released them, and the atmospheric circulation patterns that transported them across continents. Dust from the Sahara Desert nourishes rainforests in the Amazon. Particles from volcanic eruptions circle the globe for years before settling into sediments that will preserve them for millions of years. The dust we breathe today includes materials that have been cycling through Earth systems for billions of years. But the analytical techniques that can identify the geological origins of dust particles cannot detect whether those particles were once part of artificial structures created by intelligent beings. A flake of paint from an ancient mural becomes indistinguishable from a fragment of natural mineral pigment, once both have been weathered to their component molecules. A particle of corroded metal loses all trace of its artificial origins once it has been oxidized back to the ore minerals from which it was originally extracted. This invisibility of artificial origins in sufficiently weathered materials suggests that we are constantly surrounded by the dust of vanished civilizations without any way of recognizing it as such. The soil in which we grow our food, the sediments that accumulate in our rivers, the atmospheric particles that create our sunsets might all contain substantial contributions from the decomposed remains of technologies and structures that once represented the highest achievements of forgotten intelligences. The concept of identity dust becomes even more poignant when we consider that biological organisms also return completely to anonymous particles after sufficient time has passed. The calcium in our bones was once part of ancient sea creatures. The carbon in our bodies was once incorporated into primordial forests. The water in our cells has been cycling through countless other organisms across geological time. We are temporarily organized collections of materials that have supported many other forms of life, and will continue to do so long after our individual identities have been forgotten. Yet something persists beyond the dissolution of individual identity into universal dust. Patterns of organization, ways of arranging matter and energy, approaches to solving the challenges of existence. These abstract principles can survive the physical destruction of the systems that originally expressed them. Evolution preserves successful strategies in the genetic code of surviving organisms. Culture transmits useful knowledge across generations through stories, technologies, and institutions that outlast their creators. Perhaps the deepest form of identity preservation is not material but informational, not the persistence of particular structures, but the continuation of organizing principles that can be rediscovered and re-expressed by later intelligences working with the same basic materials and confronting the same fundamental challenges. The mathematics discovered by ancient civilizations can be rediscovered by modern ones. The technologies developed to harness natural forces can be reinvented by societies that never heard of their original creators. This informational continuity suggests that the dust of identity might actually preserve more than we initially realize, not as physical traces, but as patterns encoded in the very structure of reality itself. The solutions that intelligence discovers to problems of energy, materials, organization, and meaning might become part of the universe's repertoire of possibilities, available to be rediscovered by any sufficiently sophisticated mind regardless of when or where that mind develops. Modern physics suggests that information might be more fundamental than matter, that the patterns of organization we call particles and forces and fields might actually be expressions of underlying informational structures that persist even when their physical manifestations are transformed beyond recognition. If consciousness represents a particular type of information processing system, then the informational patterns that characterize intelligence might survive the physical destruction of individual brains and civilizations. The dust of identity thus becomes not just a metaphor for the impermanence of individual existence, but a reminder that identity itself might take forms that transcend the physical structures through which it is temporarily expressed. We are patterns as much as particles, processes as much as substances, temporary organizations of matter and energy that participate in larger patterns of organization that extend across scales of space and time far beyond our individual existence. In this view, the forgetting of ancient civilizations might be less complete than it appears. Their identities might persist not as recoverable historical information, but as contributions to the growing complexity of planetary systems that continue to support the emergence and development of intelligence. Each forgotten civilization might have added new possibilities to the Earth's repertoire of ways that consciousness can organize matter. new approaches to the challenge of creating meaning and purpose in a universe that tends toward randomness and decay. Our future written in the dust of those who came before us, their experiments with the possibilities of intelligence preserved, not as monuments or artifacts, but as expanded opportunities for consciousness to express itself in forms they could not have imagined, but which build upon the foundations their own explorations, established in the patient dust that connects all expressions of mind across the vast and patient cycles of cosmic time. Geology sometimes presents us with anomalies that resist easy explanation, unusual isotope ratios that don't match expected natural patterns, magnetic field orientations that seem inconsistent with known geological processes, rock formations with geometric regularities that appear too systematic to result from random natural forces. These strange signals embedded in stone challenge our understanding of what processes can create organized patterns in the Earth's crust, and raise intriguing questions about whether some geological anomalies might preserve traces of ancient intelligence rather than exotic natural phenomena. The interpretation of geological anomalies requires careful balance between known natural processes and openness to possibilities that might expand our understanding of what can occur in the Earth's complex systems. New discoveries regularly reveal natural phenomena that were previously unknown: self-organizing crystal formations, mineral structures that grow according to mathematical principles, chemical processes that create apparently artificial patterns through purely natural mechanisms. But this expanding catalogue of natural possibilities makes it increasingly difficult to identify truly anomalous geological features that might require explanations involving conscious intervention. Each apparent anomaly must be evaluated against an evolving background of natural processes that are themselves often more sophisticated and organized than early geological theories predicted. Isotopic anomalies provide some of the most intriguing examples of potentially significant geological signals. Isotope ratios in rocks and minerals reflect the conditions under which they formed, preserving information about temperature, pressure, chemical environment, and nuclear processes that operated during their formation. Natural variations in isotope ratios follow predictable patterns based on known physical and chemical processes. Occasionally, however, geological samples exhibit isotopic signatures that are difficult to explain through conventional natural processes. Unusual concentrations of rare isotopes, distinctive ratios that don't match expected equilibrium values, or sudden changes in isotopic composition within stratigraphic sequences can challenge standard geological interpretations and require exotic explanations involving rare natural phenomena or previously unknown processes. Some researchers have suggested that certain isotopic anomalies might preserve traces of ancient nuclear technology. Artificial nuclear reactions that created distinctive isotopic signatures now preserved in geological formations. The natural nuclear reactors of Oklo demonstrate that controlled nuclear fission can occur in natural geological settings under specific conditions, creating isotopic patterns that differ from normal background values. If natural nuclear reactors can operate under certain geological conditions, then artificial nuclear reactors created by ancient civilizations might have left similar isotopic signatures in surrounding rocks. The challenge is distinguishing between natural and artificial nuclear processes based solely on their isotopic fingerprints, particularly after millions of years of subsequent geological modification. Magnetic anomalies present another category of potentially significant geological signals. The orientation and intensity of magnetic fields preserved in rocks reflect the Earth's magnetic field conditions at the time of rock formation. These paleomagnetic records reveal information about continental drift, magnetic field reversals, and regional geological processes that affected magnetic minerals during rock formation. Unusual magnetic patterns that don't conform to expected paleomagnetic behavior might indicate artificial magnetic fields created by ancient technologies. Large-scale electrical installations, magnetic materials processing, or electromagnetic devices might have created local magnetic field anomalies that became preserved in rocks that formed during or shortly after their operation. Structural anomalies in rock formations provide visual evidence of unusual geological processes that might have artificial rather than natural origins. Geometric patterns in mineral deposits, unusually regular spacing of geological features, or rock formations with symmetries that seem unlikely to result from random natural processes, occasionally challenge conventional geological interpretation. The Richat structure in Mauritania, sometimes called the Eye of the Sahara, displays concentric circular patterns that initially led to speculation about artificial origins, though it is now understood to result from natural geological processes involving differential erosion of sedimentary rock layers. Similar circular and geometric patterns in other geological formations continue to generate discussion about the range of natural processes that can create apparently artificial patterns. Crystalline formations sometimes exhibit organizational principles that seem to transcend simple chemical self-assembly processes. Complex crystal structures with multiple levels of hierarchical organization, mineral formations that display mathematical relationships in their proportions and orientations, or crystalline networks that seem to function according to information processing principles might preserve traces of technologies that worked with crystalline properties in ways we don't fully understand. The challenge in interpreting these strange signals lies in developing criteria for distinguishing between natural processes that produce seemingly artificial results and artificial processes whose traces have been so thoroughly modified by subsequent geological activity that they appear natural. This requires interdisciplinary collaboration between geologists, archaeologists, and specialists in various technologies to develop frameworks for recognizing different types of artificial signatures in geological contexts. Advanced analytical techniques are beginning to reveal information about geological processes at previously inaccessible levels of detail. Microanalytical methods can detect trace element concentrations and isotopic ratios in microscopic samples. High-resolution imaging can reveal structural details in minerals and rocks that preserve information about formation processes. These techniques might eventually allow detection of artificial signatures that are currently below the threshold of recognition. Perhaps most importantly, the study of strange signals in stone reminds us that the boundary between natural and artificial processes is not as clear as we might assume. Intelligence works with natural materials and natural forces, often in ways that enhance or redirect natural processes rather than opposing them. The most sophisticated ancient technologies might have achieved such harmony with geological processes that their signatures became indistinguishable from natural phenomena. In learning to read these ambiguous signals, we might discover that intelligence has been experimenting with geological processes for far longer than we have imagined, leaving traces in stone that speak of ancient understanding of how consciousness can work with the fundamental forces that shape planetary systems. The strange signals embedded in Earth's rocky archive might be trying to tell us stories about the long collaboration between mind and matter that extends far deeper into geological time than our current theories of human development suggest possible. Speculation is a labyrinth, and we have wandered deep into its winding corridors. Each step forward reveals not answers, but doorways to new uncertainties. Each possibility we consider raises 3 more questions, like ripples spreading across still water. Could we ever know for certain what came before the ice? Or is doubt itself the natural state when we dare to explore the furthest reaches of deep time? Think of it this way. When you hold a fossil in your palm, perhaps a trilobite, its compound eyes still catching light after 400 million years, you are not holding certainty. You are holding a question mark carved in stone. This creature lived, yes. It died, yes. But what did it see? What world surrounded it? What songs did the ancient oceans sing? The fossil offers evidence, but evidence is not the same as knowing. Evidence is simply permission to wonder. And so it is with the traces we think we see of something greater, something older than our recorded history. The platinum anomalies buried in sediment layers, the impossible precision of certain megalithic sites, the way certain myths seem to carry memories too deep for human storytelling. These are not proofs. They are invitations to enter the labyrinth of possibility, knowing we may never find our way to its center. Perhaps this is how it should be. Perhaps certainty would rob us of something essential, the sweet ache of mystery, the gentle vertigo of standing at the edge of the unknowable. When we imagine ancient civilizations rising and falling before our own ancestors learned to make fire, we are not seeking to solve a puzzle. We are learning to live comfortably with questions that have no clean answers. Consider how doubt shapes the very nature of discovery. The archaeologists' trowel moves slowly through layers of earth, not because they know what they will find, but because they don't. The paleontologist studies microscopic pollen grains, preserved in rock, not to confirm what they already believe, but to be surprised by what they never expected. Doubt is the engine of wonder, the force that keeps us digging deeper, looking closer, asking better questions. In the labyrinth of deep time, every corridor looks familiar until you realize you have never been here before. The earth keeps its secrets not out of cruelty, but out of patience. It knows that some truths are too large to be grasped all at once, too profound to be understood without first learning to embrace uncertainty. The planet has watched species rise and fall for 4 billion years. It has seen continents drift apart like lovers in slow motion, seen mountains grow and weather away to dust. If there were others before us, builders, dreamers, civilizations with their own hopes and fears, the earth would remember them the way it remembers everything else, not in words, but in silence, not in stories, but in stone. And maybe that is enough. Maybe the labyrinth is not meant to be solved but to be walked, step by uncertain step, with wonder as our only compass and doubt as our most honest companion. Maybe the question is not whether we can ever know for certain what came before, but whether we can learn to find peace in the spaces between knowing and not knowing, in the gentle mystery of deep time itself. We are explorers in a maze made of millennia, and every turn we take leads us not closer to answers, but deeper into the beautiful, endless complexity of questions. And perhaps, as we wander these corridors of possibility, we begin to understand that doubt is not the enemy of knowledge. It is knowledge's most patient teacher, showing us that the deepest truths are often found not in what we can prove, but in what we dare to imagine. If supercivilizations fell before us, their story is not only about the past, but also a mirror of what may come. We too may vanish, leaving only traces for a future intelligence to wonder about. In the quiet hours before dawn, when the world feels most fragile, this thought settles over us like morning mist, gentle, inevitable, and strangely comforting. Picture this somewhere in the distant future. Long after our cities have crumbled and our satellites have fallen silent, another species discovers the remnants of what we built. Perhaps they find fragments of our smartphones, those ubiquitous rectangles that once held our entire lives, now transformed by time into curious crystalline structures they cannot quite understand. Perhaps they puzzle over the massive concrete foundations of our skyscrapers, wondering what kind of beings could have moved such enormous stones with such precision. Perhaps they develop theories about us the way we theorize about those who might have come before, part archaeology, part mythology, part wishful thinking. Would they recognize us as kin? Would they see in our ruins the same dreams that drive them? The longing to build something lasting, to reach beyond the boundaries of mortality, to leave a mark upon the world that says we were here, we mattered, we tried. Or would we be as alien to them as the hypothetical ancients are to us, incomprehensible minds that somehow learned to bend matter and energy to their will before vanishing into the geological record like whispers absorbed by stone? The mirror works both ways. When we imagine lost civilizations, we are also imagining ourselves lost. When we wonder what technologies they might have possessed, we are wondering what technologies we might yet discover. When we ask what could have caused their extinction, we are asking what might cause ours. The questions we pose to the past are the same questions the future will pose about us, and perhaps this is why the mystery feels so urgent, so personal, so hauntingly familiar. Think about what we are leaving behind right now, in this very moment. Our plastic particles are settling into sediment layers that will persist for millions of years, creating a distinctive signature in the geological record. Our radio waves are traveling outward at the speed of light, carrying fragments of our music and voices into the cosmic dark. Our nuclear isotopes are embedding themselves in the atomic structure of the planet itself, writing our presence into the very elements of which the Earth is made. But what about the subtler traces, our dreams, our stories, our ways of seeing the world? Will future archaeologists be able to reconstruct not just what we built, but who we were? Will they understand that we loved beauty enough to plant gardens we would never see mature, that we told stories about other worlds because this one sometimes felt too small to contain our longings, that we spent our brief lives reaching towards something greater than ourselves? Perhaps they will wonder, as we wonder now, whether we ever suspected our own impermanence, whether we knew that our time was limited and chose to build anyway, to love anyway, to dream anyway, whether we understood that civilizations, like seasons, are meant to change, and that there is a strange nobility in accepting this cycle rather than fighting it. The mirror of deep time reflects not just our possible future, but our present moment of choice. Right now, we are the ancients of tomorrow. Right now, we are laying down the traces that some distant intelligence will puzzle over. Right now, we are writing ourselves into the stone memory of the planet, not through grand monuments alone, but through every small act of creation, every moment of wonder, every question we dare to ask about the vastness that surrounds us. And maybe this is the real message hidden in the mirror of possibility, not that civilizations must fall, but that they must rise. Not that we are doomed to repeat the patterns of the past, but that we are free to write new patterns, knowing that our chapter in the Earth's long story is both precious and temporary. We are the inheritors of 4 billion years of life learning to know itself, and someday we will be the inheritance we leave behind. In this way, the lost civilizations we imagine are not separate from us. They are us, viewed from the far shore of time, reminding us that consciousness is a gift that travels from age to age, taking new forms but never truly disappearing, always finding new ways to ask the eternal questions. Who are we? Why are we here? And what beautiful things might we build together in the time we have been given? Civilizations may end, but echoes linger, myths, anomalies, whispers in stone. The long echo reminds us that nothing truly disappears. It transforms, waiting to be rediscovered. Listen carefully to the world around you, and you might hear it, the faint reverberation of something that was, bouncing through the centuries like sound waves in a vast cathedral, growing softer, but never quite fading to silence. An echo is not the original sound. It is something transformed, the same voice, but changed by its journey through space and time. When we find a myth that speaks of flying machines in ancient texts, when we discover construction techniques that seem impossibly advanced for their supposed era, when we encounter star maps carved in stone by people who supposedly had no telescopes, we are not necessarily hearing the original voices of lost civilizations. We are hearing their echoes, altered by countless retellings, distorted by the passage of millennia, but still carrying within them some essential frequency of truth. Think about how stories travel. A grandmother tells her grandchild about the old ways, the time before, when things were different. The child grows up and tells their own children, but the story has changed slightly, details forgotten, meanings shifted, new elements added to make sense of a world the grandmother never knew. Generations pass, and what began as memory becomes legend. What began as history becomes myth. But something persists, some core of truth, wrapped in layers of transformation, like a message in a bottle that has drifted across an ocean of years. The Aboriginal Australians speak of the Dreamtime, when ancestor spirits walked the earth and shaped the landscape. These stories, passed down for 60,000 years through oral tradition, contain startlingly accurate descriptions of geological events, of coastlines that existed before the last ice age, of landmarks now buried beneath rising seas. The echoes have preserved knowledge that our written records cannot match, carried forward not in books or databases, but in the living memory of human voices speaking to human hearts. In the temples of Egypt, we find references to the Zep Tepi, the first time when gods walked among mortals and the foundations of civilization were laid. In Mesopotamian texts, the Anunnaki are described as beings who brought knowledge from the heavens. Hindu scriptures speak of the yugas, vast cycles of time when advanced civilizations rose and fell like tides. Are these myths? Are they memories? Perhaps they are both, transformed by time into something that serves a deeper purpose than mere historical record. Reminders that the present moment has always been built upon the ruins of what came before. The echo travels through more than stories. It lives in the anomalies that make scientists pause and reconsider their assumptions. The precision, cut megaliths that fit together without mortar, their massive weight moved with techniques we still cannot explain. The Antikythera mechanism, a bronze clockwork computer from ancient Greece that tracked celestial movements with an accuracy we thought impossible for its time. The Nazca lines, vast drawings etched into the Peruvian desert that can only be fully appreciated from the sky, created by a culture that supposedly never learned to fly. These are not proof of ancient astronauts or lost super technologies. They are something more subtle and more profound, evidence that human ingenuity has always been more capable than we assume, that our ancestors' minds were no less brilliant than our own, that knowledge can be discovered, lost, and rediscovered in cycles we barely comprehend. The echoes suggest not that the past was more advanced than the present, but that advancement itself is not a straight line but a spiral, circling back on itself in patterns too large for any single generation to perceive. And what of our own echoes? What will remain of us when our time becomes deep time, when our certainties become someone else's mysteries? Perhaps our satellites will be the Nazca lines of the future, incomprehensible patterns traced across the heavens. Perhaps our internet will leave traces in the magnetic fields of the Earth, a ghost library of all human knowledge, waiting to be decoded by minds we cannot imagine. Perhaps our music, our mathematics, our dreams will transform into myths that future civilizations will tell about the strange beings who once lived on this blue world, who reached toward the stars while their feet were still planted in the soil. The long echo teaches us that nothing truly ends. It only changes form, moving from substance to story, from fact to legend, from memory to myth. And in that transformation, something essential is preserved, not the details perhaps, but the deeper truth that consciousness has always been here, always been reaching, always been asking the same eternal questions. The echo carries not information but inspiration, not answers but the reminder that it is good to wonder, good to build, good to dream of something greater than ourselves. Listen closely. Can you hear it? The long echo of all who came before, whispering across the centuries, you are not alone. You have never been alone, and someday your voice too will join this eternal conversation, transformed but not lost, changed but not forgotten, adding your note to the endless song that consciousness sings to itself as it travels through time. In the end, the Earth remembers in ways we cannot. Its memory is not words, but silence, not books, but stone. If an ancient supercivilization existed before the Ice Age, then we walk daily upon its forgotten remains, and every step we take is a step through layers of time so deep that our own history becomes a footnote in a story too vast for human comprehension. The planet remembers differently than we do. We remember in fragments, moments of joy, faces of loved ones, the taste of summer rain. Our memories fade and blur, becoming impressions rather than photographs, feelings rather than facts. But the Earth remembers everything, and it remembers perfectly, though in a language we are only beginning to learn to read. Every volcanic eruption leaves its signature in ice cores stretching back hundreds of thousands of years. Every asteroid impact writes itself into layers of iridium and shocked quartz. Every mass extinction carves its story into the fossil record, marking the end of one chapter and the beginning of another. The Earth remembers the moment life first learned to photosynthesize, turning sunlight into sugar and filling the atmosphere with the oxygen that would make our existence possible. It remembers when the first complex cells began to cooperate instead of compete, creating the intricate dance of multicellular life. It remembers the Cambrian explosion, when evolution experimented with forms so strange they seem like alien artwork, creatures with 5 eyes and no brain, beings that filtered the ancient seas through impossible geometries of bone and shell. But what else might it remember? What other experiments in consciousness, in cooperation, in the art of transforming matter into meaning? If intelligence arose before us, not once but perhaps many times, in forms we might not even recognize as intelligence, the Earth would remember that too, encoding it in minerals and sediments, in the subtle chemistry of ancient soils, in isotope ratios that tell stories we have not yet learned to hear. Consider how the planet archives information. Carbon isotopes preserve the signatures of ancient photosynthesis, allowing us to read the story of atmospheric change across billions of years. Magnetic minerals align themselves with the Earth's changing magnetic field, creating a compass rose of deep time. Zircon crystals, nearly indestructible, carry within their atomic structure the conditions present when they formed, making them time capsules from the Earth's infancy. If a civilization once harnessed nuclear energy, those isotopes would still be here, embedded in the planetary memory. If they altered the atmosphere on a global scale, those changes would still be readable in the chemical composition of ancient air bubbles trapped in ice and amber. Perhaps we are not reading these memories correctly. Perhaps what we interpret as natural cycles are actually the signatures of consciousness working on scales we cannot fathom. Perhaps the mass extinctions were not random catastrophes, but planned renewals. Civilizations so advanced they could orchestrate their own transformation, choosing to dissolve back into the evolutionary process rather than resist the turning of time's great wheel. Perhaps the ice ages themselves were technologies we do not yet understand, planetary scale projects that required the cooperation of minds vast and patient beyond our current imagination. The Earth remembers in rhythms deeper than human heartbeats. It remembers the slow dance of the continents, the way they drift apart and crash together, like lovers separated and reunited across geological ages. It remembers the rise and fall of mountain ranges, the patient work of rivers cutting valleys grain by grain, the way life and landscape shape each other in endless collaboration. If consciousness participated in these deep rhythms, if intelligence once learned to think on planetary timescales, that memory would be preserved not in artifacts, but in the very architecture of the world itself. And we are part of this memory now. Every breath we take adds carbon dioxide to the atmospheric record. Every city we build changes the flow of rivers and the chemistry of soils. Every nuclear test we have conducted has scattered radioactive isotopes across the planet, creating a distinctive layer that future geologists will use to mark the beginning of what they might call the human age. We are not observers of the Earth's memory. We are actively writing ourselves into it, adding our chapter to a story that began 4 billion years ago and will continue long after our species has transformed into something we cannot imagine. Perhaps this is what the ancient myths were really trying to tell us. Not that gods once walked the earth, but that the earth itself is divine, a living library of all that has ever been and ever might be. Perhaps consciousness is not something that emerges from matter, but something that matter remembers how to do. Perhaps intelligence is not an accident, but an inevitability, the universe's way of knowing itself, and we are simply the latest experiment in a project that has been ongoing since the first atoms learned to dance together in the stellar nurseries of deep space. Standing here, on this spinning rock in the vastness of space, we realize that we are not separate from the Earth's memory. We are part of it. Every thought we think, every question we ask, every moment of wonder we experience is the planet remembering what it feels like to be alive, to be conscious, to be capable of love and curiosity and the deep, sweet ache of longing for something greater than ourselves. The Earth remembers, and we are what it remembers. We are its dream of walking upright and looking toward the stars. We are its dream of asking questions about its own deep past. We are its dream of consciousness wondering about consciousness, intelligence seeking to understand intelligence, the cosmos awakening to its own magnificent complexity through the tender miracle of human awareness. And if others came before us, if civilizations rose and fell in the deep time before our ancestors learned to speak, then they too were part of this dreaming, part of this remembering, part of the endless story the Earth tells to itself as it circles the sun, carrying all of us, past, present, and future, through the beautiful darkness toward destinations we can only imagine.